Thank you so much, Carlos, for presenting what Paid Forward Network is to all the attendees. I would like to introduce Dr. Rajan Chokshi. Dr. Rajan Chokshi is a Senior Production Advisor with Fathom Solutions, a software technology startup company. And he has over 35 years of experience of global experience on petroleum and software projects in the areas of multi-phase flow, artificial lift, production optimization, well performance improvement, real-time production monitoring and data analytics while working for National Oil Company, NOCs, consulting and software and global service companies in a variety of roles from petroleum engineering, research engineering, software development, project management, training, senior consulting, as a senior consultant and as a senior business leader. He has co-authored over 15 SPE papers, 2 US patents, delivered several SPE workshops and webinars globally. He has taught graduate classes at several universities on artificial lift. Twice he was selected as SPE's Distinguished Lecturer in the year 2015, 2016, and then 2018 to 2019. He has co-chaired SPE workshops on multi-phase metering, artificial lift, and an SPE forum on production issues in unconventional. He has served on the SPE with various committees such as awards and recognitions, applied data science and digital engineering curriculum, production and facilities. With that, and I came to know Rajan when I joined Paid Forward Network. Ever since we have stayed in touch with him. In fact, Ryan, who is here as well, and myself went to Galveston once to do a scribe, to serve as a scriber for one of his multi-phase metering workshop that he put out last year. So with no other comments about it, I would like to invite Rajan to start his presentation, please.
Okay, thank you very much for this opportunity. As I reconnect with lots of friends here, some new and some that I have known from the very beginning, I still remember distinctly the very first chat I had with Carlos. I believe it was in mid-2016 or so. Carlos spent more than half an hour with me on the phone, just explaining the mission of what we're trying to do. And since then, we have not remained in touch as much, but I take as many opportunities as possible to interact with friends at Paid Forward Network. And true to the mission statement that Carlos discussed, it has been very, very helpful in more than one ways. So again, I appreciate very much. Now, today's presentation, am I presenting? Okay, let me share my screen. Host disabled, participant screen sharing. Salim, do I need to do something here different?
Is that with you now, Carlos?
Yeah, Francisco.
Francisco, you take over and give him the permission. Make him one of the co-hosts, please. Francisco, can you hear us?
You can give him the co-host.
Okay, Francisco is there.
It's done.
Okay. Is Rajan one of the co-hosts?
Okay, I can do that now.
Okay, now you can go ahead and do it.
Perfect.
Sorry about that.
Break a leg, Rajan.
Okay, thank you so much. So it's a great to revisit with everybody. What I'm going to present are excerpts from some of my trainings, some of the observations that I have captured. I was fortunate to be a lecturer on SPE lecture circuit a couple of years after I joined Paid Forward Network program, and some of this I have shared with worldwide audiences, and some of that I just put together in last couple of weeks or so. And this material has been culled from variety of training programs that I have offered, lectures I have offered. Some of that has come from one of my former employer, Weatherford, that I need to acknowledge. And lots of it has come from industry literature. As and where possible, I have identified the sources. So when you all decided to join this, my promise was that we will talk about artificial lift trends. And I said that, okay, we are going to talk about post-COVID era trend. And nowadays it's a kind of fashionable to throw in COVID in everything. But it's, trust me, it is not just that. What I have observed is that because of some of the new work patterns that we have now in place, work pattern as well as our home patterns, some of the things that I have been talking about for more than 15 years are now coming to fruition. So I'll try to talk about some of that. So keeping in mind that synopsis, what I'm going to cover here is some introductory on artificial lift, what, where, why, when, and how. Now, many of you would know a lot about artificial lift, and for you, if you are one of them, then you'll find that this is a bit introductory. Please bear with me. Whereas for some of you who have just passing acquaintance, you might feel that you are sitting in a bullet train and the stations are passing by, because I'm trying to cover a significant amount of material over here, whatever we have, a couple of hours or so. I hope I will not go over the time. So I'll talk about typical lift approaches and why we need to be atypical. I'll give you a quick description on each of the methods and peculiarities. Hopefully I'll be able to point that out. Then I will pick few slides from my 2016-17 distinguished lecture series, which is unconventional, how it challenged the classical artificial lift approach. Particularly, I want us to focus on lift life cycle choices. Again, I won't be able to focus as much. And then the final topic, post-COVID, I would say accelerators for artificial lift. And it's not only artificial lift, it's a production paradigm that I would be talking about. A couple of takeaways. DOF, if you do not know that acronym, it's a digital oil field. It's here to stay. And then I'll very briefly touch upon AI, ML, and edge analytics. Initially, when I was discussing with Salim doing this, I was thinking of doing a workshop. And I might still do that. And that workshop would be more like all of us trying to do something with the machine learning. And maybe first quarter next year, we'll plan something along those lines once I have necessary material in place. So first thing first, what, where, why, when, and how. And if you do not want to follow the rest of this material, your takeaways from this subsection should be any oil or gas well in any operating environment, anywhere in the world, needs one or more lift system during its life cycle. That's my one statement that tells you about how important this technology is. Another thing that I should have added here is that most of the wells in the world stay on artificial lift for most of their life cycle. There are very few wells in the world that do not get impacted by artificial lift. Considerations when you talk about artificial lift, you have to focus mostly on the hydraulics. Of course, you have to know mechanical, electrical side of the equation, and environmental, of course. And that's what makes artificial lift somewhat unique in the sense that there is not a single discipline that teaches you. Even though people say, I'm a production engineer, so you'll find that they will always have a niche area that they know about it. Even within the artificial lift community, you'll find that some people focus exclusively on electrical submersible pump, other focus on gas lift, and so on and so forth. Because of this diversity of the knowledge that is required, right? But the base thing is that we need to learn to work with the boundaries. Some of the boundaries are natural boundaries, meaning the reservoir pressure, whatever are the reservoir parameters, and some are the man-made. Man-made meaning we have to focus on what type of infrastructure we are putting in at the surface. And then the last part is that artificial lift comes into being because we are trying to balance business needs against the system constraints, meaning what reservoir can give us, what our facilities allow us to produce versus what are the business needs. And that is the gap that artificial lift tries to fill in. So with that, takeaways, This is a typical conventional well lift life cycle. As we saw, there is a ramp up and then plateau period. Plateau period may be somewhat longer. As I said below, these timelines are not to the scale. I just expanded or contracted to make some point. But invariably, each and every oil or gas well will have a decline. And decline is the period where the artificial lift can begin to assist. And then oftentimes I have had this argument with some people in the world that why do I need artificial lift for gas well? And there is an important reason for it. You have to remove liquid because artificial lift is all about removing the liquid from the well bore, right? So you have to remove liquid even in case of the gas wells. And that's why you need artificial lift for gas well. So that was a conventional. Unconventional came into the scene in last 12, 15 years or so. And what we see is that the production profile is sharply different. And because of this different profile, artificial lift choices and considerations are completely different. And I co-authored one paper on this, and that was a thrust of the talk. So I'll come back to this theme. But we have to keep in mind that this production decline is what forces us to think about artificial lift. Now, if the question comes up, how many wells in the world are in artificial lift? The statistics in the US has been fairly constant. World Oil has stopped publishing the statistics since 18 or so. But roughly every year they come back and say that between 500 and 550,000 wells in the US are on artificial lift. Okay, this number has remained constant in US. And my gut, based on the estimates that I see in the literature, this number has not changed even after 2017 or 18. On the contrary, that percentage might have gone up, I would think. Worldwide, this is estimate from one of the service companies in 2013. The numbers in US, it says about 540,000 or so. My estimate based on my consulting work and collaboration with other partners in the world is that the numbers in the US are fairly static, but rest of the world, it is increasing rapidly. For example, I'm working with one Middle Eastern national oil company, and we are looking at just 1,800 artificially lifted wells in one country. And that is just one lift type, right? 1,800. I estimate that that particular company, that particular country has more than 2,500 wells on artificial lift, whereas here we are showing almost entire region having 2,600. I was giving part of this talk in Argentina, and I was pointed out that, hey, 13,000 is, there is in one particular basin, they have more than 30,000 wells. So my point is that worldwide artificial lift well population, if I had to make a guess, is close to 1 million or so. And that tells you how much important this technology is to the bottom lines of operators. Okay. So why do you need artificial lift system? You need artificial lift system in greenfield and unconventional for production acceleration. Otherwise, you can say that we have some field development challenges, infill drilling, EOR strategy changes. That's when you'll want to put artificial lift. But the conventional view has been that we need, whenever we have tired production, reservoir pressure declines, water cut increases, that's when the things get difficult. And I'll come back to this in a minute. So we need artificial lift to help the tired production. But more and more, we are seeing that artificial lift is also used to help the green production, meaning for the production acceleration. And part of that is also production optimization, when we try to do that. Now, here is a small example based on one consulting work that was done more than 12, 15 years ago, where one Latin American field was studied. And the production profile, if it was produced over natural flow over the period of about 8,000 days or so, then this is what is the production profile would be, and this is the total ultimate cumulative production would be. If you put gas lift on the same field at different stages in the life, you see that this is the production bump up. And if you put electrical submersible pump system, then this is. Now, your takeaway should not be that the ESP is better than the gas lift based on this one. It happens to be this particular field was, the conditions were more amenable to ESP, okay? So, but the point of this slide is that artificial lift helps you extend the not only productive life of the field, but it impacts the bottom line of the companies. So that is important of artificial lift as a production optimizer, right? When do you need artificial lift? As I alluded to earlier, we want to bring the fluids to the surface when the reservoir energy is not sufficient, or we are trying to bring more flow quantities than what would come to the surface naturally, right? So if we have to make just a small equation, then whenever the bottom hole pressure, the pressure at the end of your valve bore is less than the sum of the pressure losses inside the valve bore and what is required at the valve head. That is when you have to have artificial lift. And if you go into some of the fluid mechanics aspects of it, then this is the basic equation. If you make a free body diagram of the valve bore, then this is the equation that you will start with. Somebody can say that, yeah, we can start with the Navier-Stokes, but this is what it will break down to. But what this says is that the total valve bore losses amount to elevation losses, friction losses, and acceleration losses. Acceleration losses, for the most part, we can ignore unless it happens to be gas valve. Most of the time, we are focused on elevation and friction. In the vertical, as well as even the highly deviated valve bores, the elevation losses rule the roost, meaning those are the losses that we need to account for in our artificial lift calculations. Friction losses become significant once you go into the lighter phases, gas valves, or you have extremely small size of the valve bore through which the valve fluids have to flow. So this is a kind of, and this is the only equation that I'm going to show in this presentation, just to make a point that this is all about the hydraulics, artificial lift. And you have to throw in some electrical engineering or some mechanical engineering, depending upon the lift method that you're looking at. Here is a picture of the subsea. It is slightly more challenging, but the principle remains the same. You have to account for the valve bore losses. In case of subsea, you have to account for the losses from the seabed all the way to the top side. But fundamentally, all you're trying to do is how do we provide what is considered additional total dynamic head, or TDH. So this is one new term. You said, wait, you never talked about TDH. What is TDH? Okay, so TDH is, as this picture shows, you have one boundary, which is the reservoir pressure, another boundary, which is the wellhead pressure. Now, this wellhead pressure is influenced by your surface facilities, what type of flow lines you have, what type of separation pressures do you need to hold. So these are the two boundaries that I would keep focus on for the time being. Then as the fluids flow through the reservoir, you have bottom hole flowing pressure. Most of the artificial lift engineers, they focus on the hydraulics in this area, right? And they typically use a simpler expression for the reservoir flow, which is some kind of Vogel expression or straight line PI in some cases even. But what happens, as you know, is that currently this gradient curve shows you that the well is flowing with whatever fluid rate that we have considered for this gradient curve. But the moment reservoir pressure starts declining, well, the reservoir losses increases, your bottom hole flowing pressure will decline, then what will happen is that the new conditions would be like this. Now, in this case, as you can see, the fluids will not flow to the surface, meaning you have to lower some form of artificial lift. And this artificial lift will provide this type of bump up or boost in the pressure. And this boost in the pressure is called total dynamic head, right? So the artificial lift design or the planning problem is about figuring out how much of this total dynamic head we need to provide. It's not only design and planning problem, it's also operational problem, in the sense that once you have lowered the artificial lift in the system, you have to also keep tabs on it, that does it continue to provide this total dynamic head as was promised or not. And how do we know about those things? You have to have some kind of measurements. And I'll come back to that measurement theme more towards the end of the presentation. So this is the basic concept of total dynamic head. And that's what the artificial lift, regardless of whatever method you talk about, and I'll talk about multiple of those in a minute. Okay. Next, we are going to look at some simple analysis curve. What we are looking at is a pressure versus the flow rate axis. And some of you may have worked with nodal analysis, so you will recognize that this is the inflow performance curve and this is the outflow performance curve. In this case, I have plotted this curves at the mid perforation step, meaning right in front of the reservoir. So this outflow or the green curve represents the well bore losses and what are the surface constraint, whereas the brownish, reddish, orangish color that you see here, inflow performance curve, represents the losses that occurs in the reservoir. The intersection of these 2 points is the nodal analysis equilibrium point, and this is what the valve would produce naturally, right? And I do not want to belabor this point, but just one point, that if you want to produce to the left of this equilibrium point, then reservoir energy is higher than what you need. If you want to produce to the right of it, then reservoir energy is less than what we need to produce. And typically, this is what you would identify as the total dynamic head. So instead of producing this quantity, let's say you want to produce this quantity, then this much of additional boost you'll have to provide, right? So this is the total dynamic head or boost required from the artificial lift system for that particular flow rate. The actual picture is slightly more complex than that, but for the purpose of our discussion here, this is what I'm talking about, how one can decide on the lift capabilities or what are the lift requirements, right? But the nodal analysis is the tool, okay? And again, I cannot emphasize this enough. Any of these plots are just at one point in time, meaning one set of conditions. One reservoir pressure, one wellhead pressure, one water cut, one gas oil ratio, one tubing size, on and on and on. As we all know, things do change. And what changes? I'll come to that in a few slides, right? So now let me go to the second part of my presentation where I'll give you some introductory, now that we know why, what, where, when, how of the artificial lift, I will now focus more on how, right? So I'll give you some idea about what are the different types of artificial lift methods, what are the typical surface and downhole equipment requirements, and some consideration. This is the part where we'll be kind of sitting in the bullet train as the different stations will pass by. Your takeaways from this section should be that these are all good lift methods when you apply them in the right context. That is one of the biggest problems. Most of the time, people have this mindset that just drop it and forget it. That is what we want to do. But in case of lift method, what may be good today may not be good tomorrow or over the entire lifespan. So we have to be vigilant about our lift choices, lift operating modes, and lift changeovers whenever any condition change. Meaning we need to understand our reservoir, we need to understand our field condition, we need to understand what is happening not only in the wellbore but around the wellbore. And this is one area where lift community is also becoming more and more aware of some of the shortcomings of the approaches, right? So consideration, again, I'll repeat this, that most of these lift methods, you require some mechanical, electrical, and environmental. And by environmental, I mean broader than just the Greenpeace movement. We are talking about what is the environment inside the wellbore, what type of corrosivity conditions are there. And that is what dictates what type of chemical program you need, what type of material selection you have to make, and so on. So when you think about artificial lift method, traditionally, what you're looking at are about 7 pictures, but effectively there are 8 lift methods. And I'll put the things in motion. The first one is the rod pump. That is the ubiquitous symbol of the industry. And that is where the maximum number of installations are in the world on this lift method. I'll not spend too much time describing each lift method. I'm just trying to bring up the picture to give you an idea about what type of different downhole pumping motions occur with different lift methods. So the second one in the middle of the screen right now you're looking at is a progressing cavity pumping, or PCP. The third one is the electrical submersible pumping, and this will be in the loop, so you'll keep on seeing what is happening. The fourth one is hydraulic jet and hydraulic piston pumping. The fifth one is the gas lift. The sixth one is the plunger lift. The seventh one is the capillary injection. Let me cut down on some of these volumes here. Okay, so I'm going to keep kind of this slide for slightly longer than what I would keep, just to give an idea about how these different lift methods have different surface setups and downhole setups, right? And we'll, as I describe the other individual lift method, kind of pay attention to that. That if I have to use one particular lift method, do I need a workover rig or can I use it with wireline when I have to repair it? And these are the consideration that production engineers need to constantly work with when the lift system is in operation. And here is one thing I'll tell you. Most of the production engineers are not traditionally taught these things. They somehow learn it from the old field hands. Because when you go to the engineering school, even if you go to petroleum engineering school, what you're taught are typically just some of the outlines. You're taught some of the design processes very superficially. And I know that because I'm teaching one of those artificial lift classes, right? But when the same engineer goes to the field, all of a sudden they are exposed to so many field conditions, so many constraints that they somehow get lost. And then they end up making suboptimal choices in spite of that training. And this is one of the things that I've been constantly discussing in last 15 to 20 years of my teaching all over the world, not only artificial lift, but different nuances of that. Okay. So when we come back to the different classification of this lift method, we can put them in two buckets in terms of the energy source. On the left side, you're looking at what is called plunger lift, foam lift, and gas lift. These three lift methods are primarily driven from the reservoir energy consideration, and the lift methods on the right side, just a sec, I see something going on in the chat. Hopefully I'm not expected to answer those right now. If we can keep those questions until the end, that will be good. Or
Yes.
I don't know, what is our protocol? Are we breaking somewhere in between for some questions? Or do you want me to say that, okay, we can have questions at this point?
No, Rajan, as you go on, people can put their questions in the chat anytime, but once you finish it, your presentation, after that, we'll go with the Q&A.
Okay, perfect. Very good, thank you. So coming back to this slide, what I'm trying to point out here is that depending upon how we are providing energy to the artificial lift, we can put them in two buckets. So on the left side, plunger, foam, and gas lift are primarily reservoir-driven method, meaning the energy source is, primarily energy source is the reservoir. Whereas on the right side, all the lift methods have in their name pump in it. Rod pump, piston pump, progressing cavity pump, jet pump, electrical submersible pump. Wherever you see the name pump or the pumped method, you can say that, I'm going to lower something in the valve bore which would be energized from the surface. So the energy source to drive that lift method is coming from the surface. So now when you look at the surface setup that you can see here briefly in the picture, you can see that there are different setups and different considerations that one must apply when you start installing or when you start thinking about this lift method. Do I have enough space? Is my valve pad big enough to accommodate this rod pump and so on and so forth? Okay. Now let me give you another way of classifying this lift method, which is based on the liquid production capacity. Again, lift works on lifting the liquid. It doesn't care whether it is lifting oil or water. It has to lift liquid. And one of the secrets of the world, and not a secret, we all know that most of the wells in the world are lifting what? A lot more water than a lot more oil, right? Particularly in the North America, and to a large extent, I'm seeing that trend around the globe also. So in terms of the liquid production capacity, plunger and foam lift falls into the lower end of the spectrum, meaning typically less than a couple of 100 barrels of production. You might have few outliers here and there that might say, I can produce 300 or 400. But most of the wells on plunger and foam lift would be typically producing less than 10 to 20 barrels per day. On the other end of the spectrum, you have jet lift, ESP, or the gas lift, that can go producing as high, theoretically speaking, as high as 30, 40, 50,000 barrels per day from a single well, right? In between, middle of the road lift methods are piston pump, progressing cavity pump, rod pump, and they typically are known for producing quantities less than 1,500 barrels or so. Now, having said that, you also have to keep in mind that there are upper end systems which are available that can produce at the lower end as well. Like until about few years ago, the thinking was that ESPs are good for producing more than 1,500 barrels per day. But nowadays, if you go and talk to any ESP vendor, they say, oh, we have a system that can produce even 50 barrels per day. So and then I have also worked on gas lift in Gulf of Mexico that produce as much as 10,000 barrels per day, whereas in my home country where I'm originally from, when I was working for a national oil company, there were some gas lift wells that were producing less than 10 barrels per day, right? And even here in US, we have quite a few wells like that. So my point is that even though these lift methods are known for producing higher quantity, they are equally capable of producing at the lower end of the spectrum, right? Whereas these methods, which are on the lower end, the medium end of the spectrum, they cannot go to the upper end of the spectrum because there are some physical limits of the mechanisms, the way these systems are structured and configured and so on and so forth. Okay, so now I've been talking too much, so there's a quiz for you. Which lift type has the most installation? Now, we are not going to ask you to type your answer or anything. Just pick one of the, we have discussed 8 lift methods, which I have listed here, 1 through 8. So mark your answer in your head. Which lift type has the most installation? And the answer, if you say rod lift, then you are correct. So please pat yourself on the back for me. The second question is, which lift type gets the most capital? And why this question came, I was working for a service company, and what we were doing, we were selling the equipment. So we have to keep a tab on which lift method is being preferred. So again, the choices are the same, 8 lift methods. Which lift type gets the most capital? Meaning, if you are running a service company, then okay, how many equipment or how many millions or billions of dollars of equipment would be sold in which category? So that is the question. This is on annualized basis. Okay, let me clarify that. And if you answered ESP, then that is correct. So here is one thing that tells you that even though we have most installation rod lift, ESP gets the most capital. Now this slide is courtesy of a research company called Spears and Associate, and I'm going to give them a plug because I really respect what they do. And they have a very nice blog. If you guys have not subscribed to it, Richard Spears and his brother out of Tulsa, Oklahoma, they publish these blogs on almost weekly basis. They have also a podcast, and they really present the trends that are in the service industry in a very humorous way. I like their style. So this slide has come courtesy of one of the artificial lift reports that they typically sell for about $3,000. And I requested to Richard, and he just sent me the slide deck without charging me a penny. Now that was in 2017. I haven't gone back to the till second time yet. So maybe I'll do that next year and update this slide. But the trends are not, what you're seeing here in the green is the oil field equipment and supply services budget trends. And what is the artificial lift trend? And what this says is that the total oil field equipment and service market grows, surging and growing some years, whereas the artificial lift market tend to grow around 10% per year during up years. But the down years are typically not as harsh as the broader market. And that tells you that artificial lift is required whether the market is up or down, because it's a staple of the production engineering. If you want to produce a well, you have to have artificial lift, you have to maintain it, you have to put in something new. So it is relatively not as harshly punished during the down cycle as the other lift segments are, typically like drilling or completion and such. right? This is the market size, 8 billion. I don't know what is my estimate for this year's market size would be about 6 billions or so. Overseas market is very strong, by the way. It's a domestic market. And by the way, if you have a question, who are the main players? This is somewhat dated list, and you'll find the names Baker Hughes, G. Of course, G is gone from the Baker Hughes now. Schlumberger, Weatherford, Dover. Dover is now Epiergy, Borat's. So, and Halliburton has jumped ahead because of their acquisition of Summit now. So I would put Halliburton ahead of Weatherford now. And if you see Baker Hughes, Schlumberger, and Halliburton, where from they are getting most of their capital, I mean, most of their revenue in artificial lift segment, ESPs. And that goes back to my previous slide where I said that ESP gets the most capital. And to support it further, what you're looking at is, again, courtesy of Spears and Associate research report. What you're seeing is that out of 100% capital allocation year to year, I mean, the spend year to year, the largest one is ESP. And it has been roughly about 50%. And this goes back to 2005. In between, during 2012, 13, 14, rod lift tried to gain some market share, but again, it fell back, as you can see here. So this says that ESP is the one that consumes most of the capital that people invest in. Okay, the question Rafat asked, and I just went, so I'll just address it right now. What do I mean by most capital? Meaning, if you add up all the spend on a year-to-year basis, then the spend on ESP is the highest. It is not that it's just that the technology is more expensive. But we can have that, Rafat, later on. More discussion during the breakout. Okay, so now I have another question. Which two lift technologies produce the most oil? Rod lift, gas lift, PCP, plunger lift, ESP, hydraulic jet pump, piston pump, and foam lift. If you are locked in your votes, I'll just move forward. The answer is gas lift and electrical submersible pump. If you look at, and at one point, some of these IOCs, they used to give this statistic in their annual reports or in some industry presentations. And my constant read was ExxonMobil or Shell. They would say that gas lift and ESP, gas lift, ESP. Lately, I do not see that, but the anecdotal evidence is that these are the two methods that produce the maximum of the oil on year-to-year basis because these are high volume methods. Okay, so when is the best time to select a lift method? This is a kind of a question that was, my apologies. This is one of the questions that used to come up because traditionally people always thought of artificial lift after the well is in production for several years and production starts declining and then say, we need to put some lift method. But lately, all the lift practitioners are now going in the direction of asking people that, hey, even before you drill the well, you should think about artificial lift. Because some of the drill time decisions that you make end up hurting your chances of producing that well optimally with artificial lift down the road. And I remember around 2012-13 timeframe, one of the IOCs, they invited me to talk to their drilling group to explain to them what impact some of the drilling decisions that they are making can have on the production, particularly on the artificial lift down the road. Because their production group was constantly telling them that, hey, you're putting these dog legs here that is breaking our rods apart because of the higher friction. We are not able to lower our ESP beyond this band that you're making. So I was trying to tell them that, hey, when you conduct the gyro surveys, go for higher resolution rather than low resolution surveys that typically is being done. So anyway, so the point is that before you drill the well, you should be thinking about the lift methods. Actually, lift methods should be part of the field development planning process. Okay. Moving on, When you think about artificial lift, whether you are at the selection stage, design stage, or the operational stage, you have to look at which type of asset you are operating in. This particular lift method would be operating. It's maturing field, greenfield, unconventional. Then where this well is located, is it onshore, offshore, subsea, whether it's hot or cold? And what do we mean by hot or cold? Do you have any type of cyclical steam stimulation or steam assisted gravity drainage type of going on? And believe it or not, when I was visiting Kenya, I came across some of the geothermal wells where they were also using ESPs. And as you can realize, some of those geothermal wells can have temperature upwards of 200 degrees Celsius. So you have to think of location where the artificial lift would be lowered. Location is also important in the sense that if the location is very remote or at the top of the hilltop, then how do you bring the equipment, or how would you be able to bring the equipment over there, or how would people access that location on regular basis, right? Then you have to think of what type of PVT and what type of phase envelopes the well would be dealing with on year-to-year basis. Is there too much of too little gas? Lots of water coming in? Is it going to be heavy oil or light oil? Is it going to be sandy oil? Or what are you going to do about the nasties like H2S, asphaltene, CO2, and so on and so forth, right? Next, you have to think about the reservoir. Do we have enough reservoir energy? How much of uncertainty do we have in our reservoir projections? Do we have horizontal completions? And some of this theme you will see recurring in a couple of other slides later on. Valve bore, what size of valve bore do you? This is completion size is very, very critical. And that goes back to what I was saying a couple of slides earlier, that before you drill, when you are putting the well on the paper, think about the completion size, okay? The last but one bullet on the resources, budgets is very important. If you are going to make a decision about artificial lift after well is already in the production, then most of the time those budgets are going to come out production engineering. And production engineering people have very shallow pockets, unlike drilling brethren, right? So oftentimes I tell people that, hey, we should be talking about artificial lift with the drilling people so that it comes out of their budget and it doesn't become a bigger problem, right? Then you have to think about availability of the power. What type of people do you have? What is their mindset? And this is, believe it or not, this is very, very critical point. As I go around the world talking to the people, somehow after sitting in my class, they said, but this is how we have always done it. And I try to tell them that because we have done it doesn't mean that we have to continue to do it this way. And actually unconventional has really challenged lots of this mindset in North America, and we have learned to think differently. And I'll come back to that theme later on. Production optimization is also becoming more and more important. I've been talking about this topic, production optimization, since 2007 or so when I joined one of the service companies that I was part of. And at that time, I would put people to sleep when I start talking about production optimization. And nowadays, it seems that, and this is a production optimization from the production engineer's perspective, right? And nowadays, it seems that there are lots of companies that talk about doing this using some of the edge devices, AI, ML, analytics, and so on and so forth. We'll touch upon that briefly. Okay. So what are the time-related factors that you need to take into consideration when you're talking about selection, design, or operation? As we know, with the time, reservoir pressure, productivity, and production is going to go down. Appetite for capital expenditure is going to go down. And then you have competing demands from the completion changes, surface facility changes. And then there might be enhanced recovery approaches that would require also some CapEx, right? On the other hand, on the PVT and phase envelope side, you have water cut, GOR, viscosity would be increasing as the gas comes out of solution more and more. Well, facilities would age, well would age, meaning you have integrity issues, you have flow assurance issues, and then you have to take care of corrosion, scale, sand, paraffin, asphaltene, hydrates, depending upon your environment. So these are all the factors that you have to keep in mind as you are designing, as you are selecting, as you are operating artificial lift, or as you are thinking about switching from one to another lift method, right? Some more factors, as I already touched upon people and money aspect earlier. your need for this operating resource is going to go up as the valves age, facilities age, right? Whereas the availability of the qualified operating resources will go down. Think about it. As you look around operating companies, where are the most of the qualified people sitting? In the field development group. And once the field is in operation, what quality of people are sitting in the production side of it? You do not have as many, unfortunately, we do not have that many qualified, at least that has been my observation. And then, as I said earlier, attitude for adopting different approaches also, if it doesn't go down, it does not change. That is what I see, right? And then the operating expenditure continuously goes up. And these are real constraints against which artificial lift environment has to operate. Meaning we need to continuously be vigilant. We have to monitor the environment. We have to monitor all these factors and adjust, make continuous adjustment to accommodate for these changes. In order to do that, you require qualified people. In order to do that, you require people who understand the interplay between all these factors, and then come up, then be nimble on the field. And these are some of the things that operating companies are realizing now. And there is a more emphasis on doing some of the production optimization using remote monitoring and such that, okay? So the question is, how do you go about applying the artificial lift technologies, right? You have to start by understanding reservoir. What are your target production levels, condition? What are the surface constraints, right? So that is where you do some reservoir analysis, valve bore analysis, nodal analysis. These are the first 3 steps you have to do. And that's what we do in field development typically. But my point is that this needs to happen throughout. Then you have to eliminate technically infeasible lift technology, which lift methods work, which do not work, based on the required performance, based on the availability of the support infrastructure, skill base, and so on and so forth. And that lift selection itself can be very interesting and challenging for some companies, right? What I'm seeing often is that this function, the second part, design function, is being transferred over increasingly to the service companies. Operating companies are saying, hey, you go and do it. Now, service companies, they have different competing pressures. I was part of that, right? So I know what could be positive and negative over there. So that's where I'll stop with my comment. Then comes the economic evaluation. You have to look at not only acquisition, but training cost, installation costs, how we are going to change our people to adapt to the new lift mindset if we are going to put in new lift, right? What are the operating costs? What is the reliability of the equipment? How we are going to replace them if we need to replace them? So these are all the consideration that needs to go into the artificial lift technology, whether you are just selecting it or you're switching over or you're already operating it, right? And the final part, the optimization approaches. This is where digital oil field related concepts comes in, and I can start throwing all the acronyms that I have alluded to: AI, ML, dashboards, and edge devices. But the idea is getting access to how my well is doing now, what I need to do so that things do not fail, what I need to do so that things continue to work the longest possible, and so on and so forth. Okay, if you are interested in pursuing this further, this is a list, rather incomplete list of commercial software available out there. And notice one thing, that there is not just one software that addresses most of the lift methods. Now somebody would agree with, may disagree with me, but in my experience, what I have found is that each software will have its own niche area, and this landscape is changing. So now you can see how the lift world is subdivided. So ESP engineer may or may not be able to work comfortably with the gas lift because they do not understand concept. They may not have used the workflows in that software. Okay. Now, this is one table that I'm presenting from my previous employer, Weatherford, where what they did was they have given a kind of cheat sheet that if I have this type of condition, which are mentioned in the left side, then which lift method would fit that bill. The purpose of this table is not to select one lift method, but the purpose is to come up with 2 or 3 lift methods that will be applicable. So this is a screening table, meaning you screen out the ones that will not work and then focus on 2 or 3 that will work and then do further due diligence, right? This is very quick intro to what is my design approach would be if I am working on a job, right? One thing I would also like to point out, this maximum value of the depth at which this lift method can operate, or maximum volume or the liquid that it can handle. These are somewhat wishful thinking numbers because they were provided by that particular lift's champion, right? So we have to take some of these numbers with a grain of salt as to their applicability. Having said that, I must also remind that the vendor community, the people who are making this equipment, they have come a lot farther and they are being constantly challenged to push these boundaries even further. Okay. So this is, we are at about roughly less than an hour time frame. Now I'm switching the gear. If you guys have a idea about taking a break, then this will be one point, or else I can continue.
Yeah, Rajan, why don't we take a short break? And in the meantime, Francisco, if you want to take a picture of the whole group with the attendees together with Rajan, why don't you go ahead and do it now?
I can do that. Look pretty, guys. And I can take a picture of your name, or I can take a picture of your nice looking features.
Okay.
Yeah, how are you coming? Okay, where is that beach? That's a nice beach. Oh, I'll go there Sunday. Okay, that's it. Everybody stays with just the name. I guess so. So I'm taking a picture. Change your mind. You have 5 seconds to change your mind if you want to show up in the picture. Okie dokie. So picture coming up. All right. All right. Now you can go back to your cave.
Okay.
Okay. Thank you so much, Francisco.
All right.
Yeah. So really, Rajan, actually, we don't need a major break. It's just
Okay.
because it's the virtual session, people can go out and come back whenever they desire.
Okay. All right. Okay. So then when I'll have to take a break, I'll just, that's good.
Yeah, please.
Okay.
Please.
All right. So guys, one more thing I need to alert you about. There is some repair work going on. So you might hear some background noises. Hopefully I ask them not to make too much while we are in the session here. But if it happens too much, what I'll do is that I'll unplug from here, go into my coat closet so that there are all the voices are muffled. Okay. And I hope my dog also doesn't go crazy. She's sitting next to me. Most of the time she's silent, but okay. So far what we have talked about are the lifted decisions that one needs to make, whether you are selecting, whether you are designing, or when you are at the operating stage. Now I'm switching the gear and I'm going into each and every lift method. I see some of the questions that have come that what is foam lift and so on and so forth. Hopefully I'll be able to respond to that. So now fasten your seatbelt and we are going to go through the blend of different lift methods very quickly. What you're looking at is a well pad. I think it's in the Eagleford area. You're looking at the wellhead with the gas lift. In the background, you are seeing some of the associated infrastructure that they have put up primarily the associated infrastructure for gas lift would be the compressor and some of the, in some cases there could be heater treated knockout drums. What you're looking here are some of the, let me see if I can blow up some, usually I have in my PowerPoint some type of thing that I can blow up the things, not blow up, I mean, okay, here we see. Okay, okay, so at the same time, so what I was trying to point out here is that here you see some of the lift optimization equipment. And for all purposes, you are seeing that this is a normal wellhead, except and there is some additional line that is going on to the backside or on the casing side, if you see here, right? And that is the injection gas. Okay, so gas lift is the first lift method that is kind of an extension of a naturally flowing valve. In naturally flowing valve, you have a fluid column weight that is reduced as the formation gas comes out of the solution with the change in the pressure and the temperature, as you are seeing on the left side. Now, in gas lift valve, what we are trying to do is that we are trying to enhance that process by injecting the gas, and let me try to, so what we are doing is that we are injecting natural gas, most of the time natural gas, that is shown in green here, into the casing tubing annulus, and that gas enters the valve bore through the special configuration called mandrel. And there is a device, gas lift valve here. The purpose of the mandrel and gas lift valve is to regulate the flow of gas inside the flowing stream, which in this case happens to be the tubing. Now keep in mind, gas lift can also be applied in the reverse configuration, meaning you inject the gas into the tubing and produce the fluid through the casing tubing annulus. So if somebody comes and tells me that, hey, my gas lift valve is producing more than 6,000, 7,000 barrels per day, most of the time I can bet money and not lose it by saying that that is an annular completion, meaning the production is coming out of the tubing casing annulus. Whereas most of the gas lift valves, the production would be coming out of the tubing. Okay, so that is a nutshell, very brief description of the gas lift. We are using gas to reduce the density, and by reducing the density, we are reducing the bottom hole flowing pressure, which in turn allows the reservoir to send more fluids into the valve bore. So the primary driver, production driver here is the reservoir energy. Okay. Moving to the downhole components, I already referred to the two, and I pointed out that there is a side pocket mandrel. This is the picture called side pocket mandrel. There is another type of mandrel called conventional mandrel. The difference between the two is that this one has a kind of kangaroo belly type of thing, whereby there is a distended section or the oval section, a pocket, which basically holds the valve, whereas in the conventional mandrel, the valve is hanging outside on the lug. So mandrel and gas lift valve. So the design problem for gas lift, as far as the valve bore is concerned, is at what depth we should lower this mandrel, what size of the valve we should lower in, and what should be the orifice inside that gas lift valve, and what type of gas lift valve. Other design decisions could be what should be the available injection pressure here, because that available injection pressure also determines at what depth we can lower. And then there could be a whole host of other decisions you have to make, what type of compressor you have to make. But this is not my gas lift class, so I'll just stop myself. So the design involves depth selection for mandrel and size of the valve. That is just one simple thing. Here is a picture on what is called conventional mandrel and what is a side pocket mandrel. And this shows clearly that the flow passage is the same in both the cases, except how do you access the valve? And this is a one important thing to note, that if you have to change the valve, then here you can use wireline procedure to pull the valve out of the hole. In this case, you have to pull the entire tubing out of the hole. And that is the difference between conventional and retrievable mandrel. Most of the offshore installation or the installations where it is expensive to service the well by workover, they would go for retrievable mandrel type of installation. Most of the onshore wells, people go for conventional minerals because conventionals are cheaper. Okay, here is a brief outline on what type of well site gas lift equipment is. This is more of a more advanced setup. It is not as advanced as I would like it to be, but still it is advanced. Most of the time we have some type of 2-pin chart recorder. That was in old days. If you are young enough to remember that, then join my company. And then you have some sort of injection choke here. Now this choke could be manual or it could be adjusted from remote location. There could be time cycle controller based choke. And the whole function of this choke is to regulate the flow inside the casing tubing annulus, right? And it is managed by measuring the differential between the tubing pressure and the casing pressure and such. So this is a brief intro to the gas lift. And here you are looking at the gas lift wells on the pad. And what you're looking at here is all the measurement related to the gas lift injection quantity, how much we are injecting in each of this well. That's what you're seeing here. So this pad-based development requires you to have some compression facilities on the pad itself, unless you have some centralized compression. And these are some of the debates that are going on in production engineering community about, particularly as we have now those super pads that are coming up with 12, 15, 20 wells on one pad and so on and so forth. Continuous, there are two types of gas lift, continuous gas lift and intermittent gas lift. Most of the time when people say gas lift without qualifying it, they mean continuous gas lift, meaning you are injecting gas into the production stream continuously. In intermittent gas lift, you are injecting intermittently. So what do we want to achieve in the continuous gas lift? You want to inject gas through the lowest possible gas lift valve. Lowest possible gas lift valve, that should be our goal. We want to prevent multi-point injection, meaning we do not want to waste the gas whereby gas enters here or here at the same time. We want to enter it only from the deepest possible point, because that is when you are utilizing the energy most, okay? You want to provide optimum amount of lift gas. Too little gas, meaning your production will not be coming out as much. So there is a production deferment. Too much of gas, you're wasting your compression energy at the surface, and that gas is not coming. On the contrary, in some cases, it can contribute to some friction losses that you do not want. So this is the whole, in this one slide talks about what is a continuous gas lift optimization problem. Details are always devilish, as somebody says. So there are lots of things, but gas lift is one lift method where you have to have very strong understanding of hydraulics as well as the reservoir performance and surface network performance. Okay, typical gas lift application scenario, as you can see on the left side, you are looking at the picture from Weatherford about the surface, onshore gas lift. On the right side, you are looking at some submersible gas lift. So point being, gas lift has been used in all parts of the world, remote location as well as subsea locations. It is used in long perforation interval. Naturally flowing wells even also use gas lift on intermittent basis. In lieu of swabbing, people sometimes just trickle in some gas with the nitrogen cylinder to kick off the valve, for example. In thermal wells also they use gas lift, and I'll not read all of that, but these are the typical gas lift application scenario. Now let's look at the second major artificial lift methods. You may recall from the previous slides that ESP, or electrical submersible pump, takes away lots of capital on annualized basis, and this is how the ESP well look like. It doesn't look very much different from a gas lift or naturally flowing well, except what you're seeing here is a cable that enters inside the wellbore through most of the time, that enters through the casing tubing annulus, right? So here you have a picture that shows slightly better setups. On the surface, you have some type of controller. There might be some transformer bank. The moment I start using transformer and controller, you know that there's some electricity involved here. There's a cable that is lowered inside the wellbore. Okay, so these are the telltale signs of ESP valve most of the time. High voltage situations, you're looking at voltages in excess of a few thousand volts, downhole voltage, right? So this requires qualified electrical engineers intervention in addition to the petroleum engineers intervention. What you're looking at is a cable that is trapped typically on the outside of the tubing, and that cable goes all the way to the bottom. There's a motor here, and let me go to the next slide that explains slightly better than what I'm trying to hand wave here. So again, starting our journey from the top, there's a cable that comes outside from the outside of the tubing. At the end of the tubing, typically the ESP, the entire assembly is hung. The topmost part of the assembly is called pump. Okay, that is where most of the lifting work happens. Then there is an intake. There may be a gas separator device here also. Then there is something called motor seal or motor protector. And then you have motor. So motor is at the bottom in the conventional setup. And then you have a downhole sensor package. So ESP being some of the most expensive installations from the beginning, they were the first artificial lift methods to get the downhole sensing packages. Nowadays, people are lowering downhole sensing packages in most all types of lift methods. But ESPs were the first one. The reason being that the power cable can also carry the signal from downhole to the surface. So reservoir engineers also love ESPs because they get to keep their fingers on the pulse of the valve. But coming back to the machinery itself, it's a submersible pump like what you might have seen in some of the valve boards for water producing valves and such, except that these are highly sophisticated devices. Visualize you have about 5 to 6 inch outer diameter, and you're trying to generate a total TDH or total dynamic head to the tune of almost 2 to 3,000 PSI, which is equivalent to about 7,000 or 8,000 feet of the water column, right? So these are very smartly engineered, and the basic design has not changed over the years. The material of construction has changed a lot, and systems are now available that can handle some of the harshest conditions. At the same time, they can also operate over widest range of the flow rates and flow conditions, right? Here is a small animation that was originally prepared by Weatherford, and then Petrobras went in and made it slightly better colors and better music. What you're looking at is this downhole, how the cable has come in the blue. You have pump, you have separator, and you have motor. You'll get some words in Portuguese here. Bomba is a pump, admissão is intake, and protector is protector or seal section. So the motor is energized. So there's a shaft inside the motor that starts turning. And this shaft is coupled to the shaft inside the protector section. As you can see, the expectation is the gas and oil mixture will come inside the intake section, which is in green here. And then if there is a separation going on, then the gas will come out of on the annulus on the back side. And now you have a pump section. As you can see, it's a centrifugal device, centrifugal pumping device, basically. And that is our very quick understanding of how this device is supposed to work. So the takeaway is that you require significant quantity of electrical power. You have to connect those devices inside the valve bore, which are hung at the end of the tubing. Meaning, if you have to change ESP or ESP fails, then you have to call rig on the valve site. And this has been one of the biggest concern of some of the companies of the world, Saudi Aramco's and Kuwait oil companies, the companies that have some of the largest electrical submersible pump, including some of the companies in North Sea as well as in Gulf of Mexico and in Brazil also, where Some of these pumps produce as much as 20, 30,000 barrels. So what is their main concern? Their concern is twofold, that whenever ESP fails, will I have rig available to pull that ESP out of the hole, and how much of production I'm going to defer in the process. In some locales, in some countries, I was told that it might take up to 3 months to schedule a rig. Now, if your well is producing 10,000 barrels conservatively, and if you do not get a rig on site for 90 days, you have deferred the production of 1 million barrels. And you can see what it can do. And that's why people are coming up with the approaches whereby they can even lower 2 ESPs in parallel, and they turn on one at a time. So if other fails, then they can do. They are also coming up with the new designs whereby they can, rather than lowering the ESP at the end of the tubing, they are trying to suspend the ESPs inside the tubing at the end of the cable or some type of capillary. And those are advanced topics beyond our current discussion, but I'm trying to make you aware of some of the trends that are happening in this part of the industry. So again, there is a pump. Each pump section adds pressure to the fluid, and pump is kind of, you can see that there are stacked up stages here. There are many stages, and the important design decision is that if I have to generate total dynamic head of 5,000 PSI, how many stages do I need in a particular assembly? And do I need 100 stages, 200 stages? And there's a whole design process, which I would love to discuss with you if you have interest, but this is not the time. So the thing is this, that at the design time, you need to know what is your expected total dynamic head requirement, not only now, but tomorrow, day after, because once each ESP has its what is called operating range. It cannot work over the entire range. So let's say one particular ESP at the design time, you say, nah, it is good to produce anywhere from 2,000 to 5,000 barrels. And tomorrow, if your production drops to 1,000 barrels, then you better start thinking about changing that ESP. Otherwise, you are going to have the failure into that system. Okay, here is a bit on the electric motors. There is significant advances in this technology. Traditionally, it has been induction motors, squirrel cage, 2-pole, 3-phase type of motor, run at 60 hertz here, 50 hertz in other parts of the world. But it can run over a wide range of frequency, and that is what allows us to produce different quantity of the fluids from the valve bore if you have what is called variable speed drive at the surface. The relatively recent advances in this technology has been what is called permanent magnet motor introduction, which are more energy efficient, which are shorter. And shorter is very important because as we go through some of the deviated valve bores, some of the horizontal valve bore with extremely high dog legs, you require as short an assembly as possible. So then your question should be, what is the assembly length in this case? It could be as high as 100 feet, 150 feet, 200 feet, depending upon the number of stages that you need to, you require in order to produce the quantity, right? So ESPs have some of those challenges. Of course, ESPs are also used in some of the most challenging environment, like up north of the border, where they are producing bitumen. They use SAGD, steam assisted gravity drainage, and there the temperature could be as high as 450 degrees Fahrenheit or 250 degrees Celsius and such. So this is where now ESP vendors have come up with the designs that can operate in those harsh environment. What is your optimization requirement? You have to understand what is a pump performance curve, and this pump performance curve is typically provided by the manufacturer, and they typically give you that, hey, between this and this range, this pump is good, right? And this is the best efficiency point. So our goal should be to keep the valve or to keep the pump producing in this range. And as soon as we start moving outside of that range, or we have to keep an eye on the pump. And so this pump performance curve is a key tool in the operation side of it, not only design, but on the operation side of it, right? You can also keep an eye on the pump health. By the way, one of the major initiative in this space has been ESP failure prediction. If you scan literature, all these big data analytics firms that come and they start talking about introducing efficiencies and such, and they will, most of them invariably will gravitate towards how they can save money by predicting when the ESP is going to fail. Actually, I've been involved in one of the projects like that with one of the Middle Eastern operator for over a year now. It's an extremely complex problem, but this lift method, because of the cost involved in bringing new equipment, in replacing the equipment, people are very sensitive to the failure of the ESP. Not that they mind failing it, it is just that when it fails, they are left with lots of deferred production. So there is a lot of activities going on in that area. Okay, so typical ESP application, as I said, high volume, that is where ESP really shines. If you are assessing a well that is going to produce upwards of 3,000 barrels, it behooves of you to seriously look at ESP. Now, I'm not saying that you should go ahead and put the ESP, but you have to take a serious look at the ESP. There are competing methods also. And ESP is used not only in oil and gas, but also in mining and water wells. Actually, some of the largest ESPs are in the mining application, where those ESPs can remove as much as 150,000 barrels of water out of a mining shaft in a matter of days. And as you can see, mining shaft volumes can be significantly higher. Okay, moving on. Now I'm going to talk about reciprocating rod lift, RRL, SRP, and the picture that you're looking at is showing there are 4 different types of surface setups and the rod pump. And it so happened that I came across this picture from Oman. In the background, you're seeing Arabian Sea, and you're looking at 4 different structural surface beam pumping structural arrangement here in just one picture. And Oman has a plenty of rod pump. So they also have ESPs, and they also have gas lift, and so on and so forth. So talking about rod lift system, almost everybody has seen this picture. And most of the discussion focuses on pumping unit, but there is a whole host of things. Pumping unit is just a surface driver. It drives what is called a sucker rod inside, and that's why this is also called sucker rod pump system. And the sucker rod is connected to the pumping unit through something called polish rod. Polish rod is called polish because it's a chrome plated, smoothest possible surface, which goes in and out of wellbore through device here that is kept. It is called stuffing box, literally stuffed with the thing so that your fluids from the wellbore do not escape out into the environment. So this pumping unit drives the polish rod. So pumping unit has a prime mover here, which is most of the time it's a motor, but it could be engine also. It's a circular motion, which is converted into the reciprocating motion. And then at the end of this long string of rods, it's a very long string. It could be up to 7, 8, 9, 10,000 feet deep. There is a pump. This is where most of the lifting work is done, right? So surface pumping unit converts the rotary movement of the prime mover to a vertical reciprocating movement to drive the pump to mechanically lift the liquid. Again, we need a pump that can provide sufficient, what's the keyword? TDH, total dynamic head, okay? So here we are focusing only on the pumping motion or pump side of it. So it has 2 valves inside, what is called a traveling valve and stationary valve. I'll not bore you with all the details, just this I could not help but show this, that how the fluid from below the pump enters into the pump chamber, and then the synchronized motion between these 2 valves, traveling and standing valve, allows to transfer that fluid from inside the pump chamber to above the pump chamber. Now this immediately tells you that as this traveling valve moves up along with the cage and the rods, we are only producing during what is called upstroke. So if you visualize At the surface, you have that horse head is going up and down. So when it goes up, that after a little bit of a delay or the stretching, you will see that this going up here, and so on and so forth. Okay. Here, what you're looking at in one picture are variety of surface configurations possible with this most popular lift method. Why this lift method is so popular? Because most of the investment for this lift technology is on the surface that is easily accessible, number one. Number two, the mechanical device is relatively simple. There's a gearbox at the surface, and then there are some lever type of arrangement, class 1 and class 3 levers. So all you have to do to maintain this device at the surface is change the gearbox oil once in a while, on regular basis, not once in a while, and provide some type of lubrication for the bearings that are there. That makes this, plus at the end of its useful life, you are still left with lots of iron that can give you some value. So which part of the world you'll not have somebody who can change the oil in the gearbox or who can grease some bearings? And that is one of the reasons why I still come across some of the pumping units that were developed in literally in somebody's backyard, not in garage, in backyard in 1930s. If you go to Bakersfield area, where Chevron and formerly Occidental, they were operating, you'll come across some of those older devices that are still working. That's the beauty of this lift method. Then you have to focus on the rod string, because rod strings are the one that take the surface energy and drives the pump downhole, right? There are a variety of constructions possible. Most of the rods are made out of steel or some kind of alloy of the steel. And API, American Petroleum Institute, has a big role in not only specifications related to rods, but also specification related to the surface pumping unit. Actually, sucker rod pumping or reciprocating rod lift is one of the oldest lift methods, along with the gas lift, I would say. ESP came onto the scene afterwards. PCP is one of the youngest one of the block, youngest kid of the block. So rod pump, because of the proliferation of the rod pumping system, API decided early on that, hey, we need to have some standards. And that's why lots of equipment has API monogram on it. And then each of the vendor, they will have their own variation. Either they have better metallurgy or some change in the design. That's how you have non-API versions of pumping unit. You have non-API version of the rod string also. So there is always some innovation that comes on. Most of the rods are 20 or 30 feet long, and they are coupled with each other using this type of threaded connection at each end. There is also called a continuous rod, which I think there is a picture in the beginning that I showed you. So here you see this. This is a continuous rod that is reeled around a wheel, and it is delivered to the valve site like that, whereas those regular rods are delivered on the flatbed in the packs of, I've forgotten how many packs do they put in, but that is how it. So here, similar to the coil tubing setup, they have also coiled rod setup. There is a gooseneck, and you are literally injecting the rod inside. So that is a different type of rod mechanism. So let me now move further. So what do we want to achieve when we have a rod pumping machine is you continuously produce as much as the reservoir will provide. This is a key thing, that as the reservoir will provide, because rod pumping systems are working on the wells in this part of the world. Most of the wells that are on rod pumping, they do not produce continuously because your reservoir is tired. So you let the influx come in for some part of the day, liquid level build up, you run your pump, and then you shut it down and let it rust and let the reservoir catch up a little bit. So that is how majority of the wells, but then there are some wells where you can produce continuously, right? And in some cases, if you have what is called variable speed drive, then you can increase the pumping speed. when the valve is capable of producing more than the lifting capacity that was sized, right? Then there are a few other considerations, what is called a fluid pound condition. Especially if you have a tired production, then it is possible that as your pump keeps on working, reservoir would not fill up the entire pump, right? In that case, what might happen is that as your plunger is going down, it will hit an empty space that is not filled with the liquid, and then all of a sudden it will hit the liquid. And that is called a fluid pound. And this type of fluid pound conditions can be very detrimental to the rod string. It can be detrimental to the surface pumping unit. In some cases, in worst case scenarios, you might see the situation where you can feel it when you're standing next to the valve head. You can feel the pump. You kind of feel it and then you hear because sound travels differently, right? So the remedy is that you either shut down the system for an adjustable time or adjust the speed to allow the reservoir to catch up, okay? So lots of optimization activity related to the rod pumping is focused on this. How do we avoid this type of situation from happening? And how do we notice a malfunction? And there are a variety of things that can be talked about, but this is not the time or place. We do not have enough time. So in summary, rod lift can be used in a variety of application, but remember they are used only in land application. So you say, why? Because of the rod. We have not come up with a reliable design of a subsurface safety valve, which is a must in all the offshore installations, subsea installation, meaning you cannot use the rod pumping for the subsurface where you require subsurface safety valve. Reason number one. Number two, as you can see on the picture, the surface pumping unit can take sizable space. There is a lot of vibration, and you'll have to make so much of space on the platform that you would not be able to accommodate rod pumping. I have seen one or two examples where people have tried to put it in extremely shallow water. It's almost like a lake and they put it, but it is never done usually in offshore applications. Offshore applications, typically ESP, gas lift, PCP are the lift methods that are being used. Okay, it is good for producing medium and light oil from any depth. You can also use it for heavy oil, but then you have to heat up the valve fluids by using either steam flood or CSS, cyclical steam stimulation, or you have to use SAGD in order to do it. And this is a very versatile lift method, and that's why it has stood the test of the time. It will continue to be that because you can use it in the market where you have infrastructure and experience, as well as you can use it in the market where you have limited skill service, limited resources and such. Okay, so now we have covered so far, if I can recap quickly, gas lift, ESP, and rod pump. Three major ones. Now we are moving into the lift methods, which are not major, but each of them have their day in the sun. So hydraulic pumping, and there are two lift methods, jet and piston pump. You're looking at some wellhead, I think this is in Bakan, if I recall correctly. And what you're looking at is a slightly different type of wellhead. I cannot go into all of the details, but this setup is required because you have to route the hydraulic fluid down the valve bore to drive the pump that is basically providing the TDH. So this setup is required basically to route that hydraulic fluid. What is hydraulic fluid? It's most of the time it's water, but after a while, it is a water mixed up with the valve fluid. So it is essentially the valve fluid. So when you look at the entire setup, what you're doing in the hydraulic lift, you're using a highly pressurized liquid. Even though I said here about fluid, it's a liquid, and you are pumping it from the surface to drive a downhole pump, okay? And so on the surface, you have a setup whereby you can have some kind of separation facilities. You have some triplex pump or diaphragm pump that can basically pressurize the liquid to the higher pressures. This separation facility, this is not called separator, this is called a reservoir, All it does is it captures the fluid that comes back from the valve bore, and it allows you to separate some of the higher end liquid, which is the water most of the time, and that higher end liquid is being basically routed back into the valve bore. And it also allows you to separate some of the sludge and things like that, so that your pump and the filters do not get plugged, right? And here is another picture from Weatherford that shows how, in this particular case, and let me see if I can blow this picture up. In this particular case, what is happening is that the red color is the power fluid. That is the convention. So the power fluid is injected inside the tubing, and then there is a bottom hole assembly in which the pump sits. Either it's a piston or a jet pump, and then the pressure is built up, and you are going to have a mixture of this power fluid with the valve fluid. Valve fluid is coming from the reservoir. So the pump provides the necessary TDH to bring both of this fluid to the surface. This lift method was somewhat marginal until the beginning of the century. And when the horizontal wells and the unconventional revolution started, this became, jet pump particularly became one of the lift methods that is used heavily for the initial kicking of the valve, because we are pumping so much of fracturing fluid down that needs to be evacuated before the production can begin. So that is what completion companies often do. So there are two types of pump possible. There is a hydraulic jet pump and hydraulic piston pump. If you focus on the hydraulic jet pump, and you might have seen nozzle venturi devices in the measurement. So this is a nozzle venturi type of pump, which relies on the momentum transfer from power fluid into the valve bore fluid to get the higher TDH. Whereas on the right side, you are looking at the hydraulic piston pump, where the pistons are driven by the power fluid. Now, both of them are hydraulic, but this jet pump has the ability to transfer larger volume. So typically jet pump is in the upper end of the spectrum. Hydraulic piston pump is in the same spectrum where the rod lift and the PCP sits, right? So this hydraulic piston pump is good for up to maybe 1,000 barrels or so of the liquid production. Whereas hydraulic jet pump can be used, one of the largest installation that I know of offshore subsea Tunisia was 32,000 barrel per day type of production. Okay, here is a picture of the jet pump being utilized in fracturing flowback application that I was alluding to earlier, whereby you can take up to 3 days for small frac volume evacuation. And this slide was prepared way back in 2015-16. Since then, we have gone for longer and longer lateral, higher and higher frac volumes. So in some cases, you might take even up to 3 weeks just to remove all the fracturing fluid. In some cases, the formation itself is strong enough, whereby after just removing a little bit of fluid, formation will start pushing the fracturing fluid out. Okay. This, I brought in this to mention one thing, that all of this lift method, oftentimes people wonder, can we use a hybrid lift, meaning combination? And jet pump is amenable to work with other lift method, and sometimes it is being used as a backup. So for example, in this particular case, let me get out of this. On the left side, you're looking at the jet pump with the electrical submersible pump. And the idea is that if ESP is not strong enough, or if ESP has failed, then jet pump can continue to work. The beauty of jet pump is that you can retrieve it just by circulation. You do not require any big workover rig, or you can do it wireline, but most of the time people do it by circulation. That's why jet pump is preferred in many of this installation. Here we are looking at jet pump with the gas lift, and this installation on the rightmost is used by BP in Alaska, or it used to be, I don't know whether they do it still or not, where one formation is supplying the power fluid to drive the jet pump to produce from the another formation. So this is a kind of interesting inverted jet pump application. Okay, so that is a brief on the hydraulic pumping method. Now let's move on to the next lifting method, which is a progressing cavity pump. People often refer to this as a progressive, and I have a beef with that. I don't think that is a correct nomenclature. It's a progressing cavity, and you will see why I'm insisting on that. What you're looking at here is a pad, and this pad is north of the border in Canada. That's where this lift method became popular first. Progressing cavity pump was introduced around 70s or so, so it's a youngest kid on the block. And why it became popular, even though the progressing cavity pumps have been around since 1930, when René Monod in France discovered what is often referred to as a screw pump also, but this is not a screw pump, by the way. There's a different category, screw pump. So why it became popular in Canada? Because of the heavy oil production, higher viscosity, lots of sand that is coming out of it. And in a minute, you'll see why this pump construction allows that. And what you're seeing here is that there is a motor that drives basically the unit, surface unit, which in turn rotates the rod. So this is also a rod-driven lift system. But unlike reciprocating rod lift, where the rods move up and down, here rods rotate. So in a way, you can think of this as that, okay, we are using the centrifugal motion, but it's not the same as centrifugal motion. So again, what you're looking at is called drive head at the surface. There is also a polish rod and stuffing box. And this rod is rotating, as I said, not reciprocating. And then below the hole, what you're seeing is a similar rod string, except the couplings that are being used here in the rod string has a different requirement, because here they are facing a lot more torque variation compared to the sucker rod pump. And then at the end, you have what is called a PC pump or progressing cavity pump. And here, this shape, people often refer to this as a screw pump because of this shape, but it is not a screw pump. So this black area that you see is called stator, and the shiny white area is called rotor, because this rotor is driven by the sucker rod pump at the surface, right? And that is where the TDH is coming from, this pump, right? And this is called a positive displacement pump, just like reciprocating rod lift is also positive displacement pump. And so is the hydraulic piston pump, right? So there are two components, as I was saying. This is the rotor and this is the stator. Stator is typically elastomeric construction, which is bonded to the steel tube. And this steel tube is hung at the end of the tubing. So just like ESP, if you have to change the PC pump, you also have to pull out. This is a traditional application. Nowadays, we have a new application whereby the entire pump is suspended at the end of the rod string, but those are few and far in between. What you're looking at here, stator, is a, sorry, not stator, the rotor is typically a helical structure of one lobe. And then the stator is a complementing helical, but with the two lobes, right? Now, if you have worked in the drilling side of the business, you might have seen some of those mud mortars. There also you have helical structures like this in the mud mortar, but there the number of lobes are more than one, okay? So now let me put this in motion to just show you how this motion looking from top. And this is the rotor, and the area between rotor and stator is a cavity. And this cavity is, when you look from the side, it will seem as if the cavities are progressing, right? And that's why the name progressing cavity pump. And when people say progressive, it kind of gets to me for that reason, that these cavities are progressive, but here it is a progressing. Okay, so that is the PCP related downhole motion animation that I wanted to show you. So as you can see, this is a highly complex motion. So the design considerations are totally different when compared to other designs. And this is something that you must be wondering as you go through this different lift method, different types of pumps, that how each pump differs from another one in the way they generate the total dynamic head. And that's why the person who is focused or specialized on progressing cavity pump, they would not be focused on ESP. They would not be as good in giving you design or the recommendation on that than the person who is focused on the gas lift. So that's why within the artificial lift community, also there are camps, people working on the rod pump, people working on the PCP, and so on and so forth. Okay, moving to the next one. This is the specialty that I was referring to earlier, that PCP can handle viscous fluids up to 100,000 centipoise. For reference, water is 1 centipoise at room conditions, motor oil 40 is 200 centipoise, and honey is 10,000 centipoise. And we are talking about 100,000 centipoise, and ketchup is 50,000 centipoise. And many of us know how we have to get the ketchup out of bottle sometime by thumping at the back, right? Because of the motion. So that is the specialty of PCP, to handle such a viscous fluid that would not even flow if you tilt this beaker, right? Another thing is that because of the construction, the stator is made out of the elastomer. Elastomer is a flexible, resilient material. So whenever you have some sand particle that comes in between the rotor and stator, elastomer gives little bit, okay? And it lets that solid particle pass by. So it can handle the sandy conditions up to 60% by volume, not continuously up to 20% or so. Now for reference, whenever people in the conventional production say that, oh, I have sandy production, the sand content may not be more than 2 or 3% by volume. It's only like when you go into this wuggy, I mean, in the Canada, when they, I'm trying to remember, they try to create the wugs, meaning they are producing sand along with the heavy oil. So that they require this ability. But having said that, you have to also keep in mind, PCP is being used in some of the application on the south of the border here in the US for lifting water out of coal seam gas or coal bed methane, okay? Because there is lots of coal fine that comes along with that water. See, we are not interested in water, we are not interested in coal fine, we are interested in getting the gas, methane out of it. But we have to remove the water, and coal fines come along with as a byproduct. So that's where PCP gets used a lot. I have also seen PCP being used in the lighter oil production situation, but there the challenge is finding a compatible elastomer, okay? So the thing about PCP system is that it is one of the least forgiving artificial lift method. If you have not done your homework, the PCP can fail in a matter of just a day or two. Here's a picture where you require, what do you see here is that power generation happening at the site, and there is a heat insulated room at the site to keep the power generation equipment, which in turn provides electricity to drive the motor here. And as you can see, with all the insulation that is wrapped around the pipe, this must be getting very cold up there, right? But coming back to the PC pump application, just like rod pump, it is also land application for the same reason, meaning you have subsurface safety valve that cannot close around the rods reliably. It is used typically for heavy, but it is also used for medium and light oil. The nasties that really impact the PC pump is the CO2, H2S, and BTX. BTX is an acronym for benzene, toluene, and xylene, the aromatics that can impact the elastomer significantly, okay? To counteract that, vendors have come up with systems where your elastomer is made entirely of metal, so that BTX, CO2, or H2S does not impact it heavily. But those are, of course, very expensive devices. And secondly, it defeats the purpose here. It cannot handle the sandy conditions as well because of the lower abrasion resistance that metallic stator would have, okay? So there are always pluses and minuses, okay? This requires skilled service resources. And another thing that we have to, like, some of you might be thinking that PC pump makes perfect sense for use in unconventional. right? Because unconventional, there is a lots of proppant that comes back oftentimes, right? And so PC would be ideal. But the problem with the PCs is that they cannot, at least the conventional PCs cannot go to the depth deeper than, even though it says 8,000 feet or so, the experienced people will tell you not more than 6,000 feet. It can go deeper. And that because we can only communicate so much of torque down below when you are torquing the rods or from the surface. And that's where people have come up with what is called ESPCP, electricals. So you have electric motor sitting at the end of the string, just like ESP, that drives the pump at the bottom, right? But again, those are more expensive devices. They're almost comparable to ESPs. So that's where it loses its, now ESPs, these ESPCPs are used in offshore Brazil, where they have some of the highest viscosity crude. And being a subsea development, they cannot use other methods, so they oftentimes use ESPCPs. So now we are switching the gears. So far we have been focusing on all the lift methods that are focused on higher liquid productions. And what do I mean by higher? More than 10 barrels per day type of liquid. Now we are going into the gas well territory lift methods. So this topic is in the gas well deliquification, and what you're looking at is, if you pay attention to some of the verbiage, or if you have worked in Australia, this is a Australian gas well site, the picture is. And what you're looking at is that there is a surface compression setup that is being used for this deliquification. I'll come back to hopefully later. But what is the problem, central problem in gas wells? In gas well, as we all know, there is always some connate water that comes, or even condensate. As the pressure drops, temperature changes, the condensate comes out of the solution and it will start falling back because condensates are heavier compared to the gas. If the gas cannot carry the condensate with it out, then over the time period, you will have more and more liquid accumulating at the bottom. Initially, gas pressure would be high enough. It will struggle through, come out in the bubble form, and it will produce. But eventually, so that is, on the surface, it will appear that, yeah, gas is coming out and there is no problem. But downhole, inside the wellbore, you have liquid accumulating. Over the time period, if you do not do anything about it, as the liquid column gets higher and higher, you will notice that not only my production has declined, but production would be erratic. The flow rates would be constantly changing. And that is a surefire sign that you have liquid loading that has gotten worse. Okay. And if you do not do anything about it, then after this unstable flow regime, you're going to have again stable, but there won't be any flow. Your well has died effectively. And this is one thing that I noticed when I was traveling through some countries where the gas production was dominant. And in some of the companies, when I was working with on a consulting, or just we were talking, what I realized is that whenever a company is led by drilling oriented people, those who are focused more on their drilling budgets and such, they do not care about bringing such well back to the production. Meaning they do not understand that there is something called gas well deliquification. Meaning if you remove this liquid, then this well can become productive as against. Whereas these people, and I'm not trying to put the whole community in bad light, but there are some people, they believe in doing optimization by punching holes into the ground, meaning optimization by drilling more wells. Of course, that would not be tolerated anymore. And that's why this gas well deliquification is also becoming more and more important, meaning artificial lift is being talked more and more about in the gas well community. I still remember I was in one of the North African country in-house conference. And to me, there was a gentleman sitting next to me. He was a geologist, of course, a geophysicist, sorry. And he said, Rajan, why you're talking about this here? We are all gas production. And then I had to explain what is a gas well deliquification is all about. But anyway, So the idea behind the deliquification is very simple, and most of the people attribute it to the Turner equation or Turner-Coleman equation, which relies on two things. That if you visualize that there is a droplet of liquid suspended into the gas stream, then the droplet is pulled by the gravity downwards, and droplet is carried upward with the gas because of the drag that the gas would exhibit, right? And that is the expression that can be further devolved into this expression here, which shows a critical velocity of the gas. So if your velocity of the gas or the production of the gas is such that its velocity is above this value given by this expression, then this droplet won't be suspended, it would be carried out of the wellbore, meaning there will be effective deliquification going on. But as your reservoir productivity goes down, as your pressure goes down, your gas flow rate goes down, what is going to happen is that this the gas velocity will fall below this critical velocity, which will result in this droplet falling and accumulating at the bottom of the wellbore. So most of the effort related to the deliquifications are focused on identifying when my gas flow rate falls below this critical velocity, right? By the way, I lied. I said earlier that that was the only equation. Here you have one more equation. So my apologies for that. What you're looking at here is that the surface tension is one of the important entity that impacts the critical velocity proportionately. Meaning, if I can figure out a way of increasing surface tension, then my critical velocity will be higher. If my critical velocity is higher, then good, I'm good, because then I'll be able to keep that well flowing for much longer time. So there are two approaches you can take. Either you can increase the flow velocity by decreasing the flow cross-section area through which your gas flows, or you can change the surface tension. Okay, you can reduce the surface tension, not increase, sorry, that was. So here is one approach called dead string and another is called velocity string. In dead string, what you're doing is to reduce the flow area is you are lowering a tubing which is blocked off at the end, meaning you are forcing the production to go through the annular space. And as you can appreciate, before lowering the string, let me go back. Before lowering the string, your gas was flowing through the entire casing space. This is how most of the gas wells start their life, right? Then once you lower the string, you are reducing the cross-section area, you are increasing the velocity, and that is what allows you to carry the fluid out of the hole. In the velocity string approach, it is exactly opposite, meaning you are lowering the tubing just like the dead string, but rather than blocking the tubing, you are blocking the annular space, meaning you are forcing the fluids to go through the tubing. So depending upon how much liquid you are trying to lift, you will go with dead string or velocity string. But we have to keep in mind, these are stopgap arrangements, okay? And that's where the question comes up of what else we can do to remove those liquid. You can use any of the method that I talked about so far. People have used gas lift, people have used ESP, rod pump, and so on. And I'll come to that. But one of the thing you can do, and this goes back to the Turner expression, where we saw that the critical velocity is proportional to the surface tension. And that's where this foam lift comes into it. What you're looking at is a surface injection of a surfactant. Surfactant is an acronym for what? Surface active agent, right? So surfactant is introduced into the wellbore, and it can be introduced into the wellbore in multiple ways, right? So you can drop what is called soap stick, literally. Rather than bars of the soap, you have bars of the soap, you have sticks of the soap. Now, soap may not be the same soap that we use to wash ourselves, but it effectively generates the foam as it comes into the contact with the liquid, and this liquid has to be water dominated. This whole foam lift works when you have water dominated production, because most of the surfactants are, I'm trying to remember, it's called aquaphilic, water loving, right? So this is one way you can just literally, as you can see here, this gentleman, by the way, he's lowering into the valve that is dead valve. So there is no HSE if somebody is concerned about that. I was told by the person who took this picture. And here is another way people do is often referred to as a backside injection. Backside injection is nothing but batch application, whereby typically you're dropping this liquid surfactant you're introducing into the casing tubing annulus, right? It is relatively simple to use, but it has a higher capital expenditure, and it works effectively. The most effective approach is using continuously, using the capillary, whereby you have a capillary string that is trapped on the outside, or it could be lowered inside the tubing, and you can insert the surfactant that way. Another benefit of using the capillary system is that you can also use some chemical additives like H2S scavenging agents or corrosion prevention chemicals or scale prevention chemicals, or paraffin removal or salt deposit, and so on and so forth. So what we are trying to do here, we are discussing foam lift, and we are saying that you can reduce the surface tension. When you reduce the surface tension, you are reducing the critical velocity. When you are reducing the critical velocity, you are allowing the valve to stay flowing for much longer period before loading up, right? That brings us to the next, and I think this is the final lift method that we are going to talk about, plunger lift. Next to the rod pump valves, the maximum number of valves, if we take count, nobody has kept that count, but my gut is that next would be plunger lift. Plunger lift is used a lot in this country for deliquification of the gas well, but it can be used for producing liquid from the oil wells as well. And what you're looking at here is a picture from, I think, Juanita, or maybe one of the basins nearby Colorado. You can see the Rockies in the background. And this is the surface setup. As you can see here, you have slightly funky looking wellhead adapter that we need to put so that we can insert the plunger. Plunger is nothing but a piston. Think of it as a piston, right? So that we can insert the plunger inside the valve. And if you recall, in the very beginning, I said that energy-driven classification, plunger lift, foam lift, and gas lift. These three lift methods are driven by reservoir energy. And plunger lift takes the cake in the sense that it is the least expensive of the lift methods. And that's why when you have a stripper valves producing less than 10 barrels of liquid, this would be an ideal lift method, provided you have sufficient gas that can drive the plunger up, right? Okay, so when you look at the downhole component, you have plunger. As I said, plunger looks more like a piston here or a pig. If you are working in the pipeline, and you might have come across the pig type of devices, right? So it essentially seals the surfaces so that the liquid that is captured above it can come to the surface as it plunger travels to the top. At the bottom, there is something called bumper spring, which is lowered using either wireline methodology, okay? And then there is a landing tool which sits inside a pump setting nipple or in some kind of profile. So this bumper spring, whenever plunger goes back inside the down, it kind of arrests it here, and there is a spring here that absorbs the plunger's shock. So this is the setup inside. When you come to the surface, as I said, it has a slightly different setup, okay? What you're seeing is a lubricator. It's called lubricator. This is where, and just like you also use lubricator in gas lift to insert and take out the gas lift valves and such. But here the lubricator stays permanently on the well site, and you can use it to retrieve the plunger when plunger comes to the surface. And then there are a few other devices. There is something called flow T. So this T section is to allow the liquid, as the plunger travels all the way up here, whatever liquid that is trapped above the plunger can kind of bypass and goes into the flow line. There's a very important function played by this device called motor valve. See, plunger lift valves typically again fall into that category of tired valves, meaning it has to build up some gas pressure inside the casing tubing annulus so that that gas can drive the plunger to the surface. So this motor valve periodically will open. As the motor valve would open, the pressure would decrease here, whereas the casing pressure that is built up because of the accumulated gas will start driving the plunger to the surface, right? So this motor valve is typically driven by some kind of controller, right? And as you can see, there is a solar panel here because you do not require any other electricity at the valve side other than the electricity to drive this controller. And you do not require a lot of electricity to drive this controller or the motor valve. And that is one of the reasons why plunger lift is one of the cheapest lift method that you can think of. And that's why it's very popular, right? So plunger lift application wise, to unload the valves that continue to load up with produced valve bore liquid, to reduce the fallback in valves being produced by intermittent gas lift. And this is where I'm going to introduce one more acronym in your glossary called PAGL. It's called plunger assisted gas lift. Some people also refer to it as a GAPL, gas assisted plunger lift. So this is where you are taking a combination of gas lift and plunger lift. And this has become popular relatively recently as we are seeing intermittent production coming from the unconventional wells. And by intermittent, I mean sometimes we get a large liquid slug, sometimes we get nothing but just the gas, and then again large liquid slug. And that's where people are gravitating more and more towards gas lift, okay? Plunger lift is also, can be effectively remove the paraffin setup from the upper part of the valve bore because it is very tight fitting with the tubing, right? So here what you're looking at is another beautiful picture from the Denver area and where they have lots of gas well application. But somebody, this guy, David Crosby, he put up a very nice test case that what are the different options do you have when it comes to remove the liquid from a gas well. You can have a free flowing well, then you can swab or intermit, you can use foam lift, you can use velocity string, you can use surface compression. I did not talk about that. I briefly mentioned it when we were looking at that Australian well. Then you can use plunger lift. There is an advanced form of plunger lift called two-stage plunger. Then I also talked about gas-assisted plunger or plunger-assisted gas lift, GAPL, PAGL. And at the end of the journey, you may go to rod lift or ESP if your liquid volumes justify it, okay? So that is a gas well deliquification. And here is a typical gas well life cycle. Initially, liquid loading happens, you are producing up the casing, then you start producing up the tubing, meaning essentially you are using velocity string concept. Then you start using foam lift. Then you use conventional plunger lift, you use stage plunger lift, and then eventually as the production keeps on going down and down and down, but the liquid keeps on increasing, you may switch over to the rod lift, okay? So far in our journey, we have looked at what, where, why, how of artificial lift, different forms of artificial lift. We have gone through the conventional landscape and how the artificial lift ends. How is everybody doing? It's about 2-hour time frame. I know. How much time do I have additional? Salim or?
Actually, Rajan, you have enough time, but it all depends on how much time you might be able to give us.
Okay.
Actually, we have this session that goes up to 12:30 with our networking, but if we continue learning from you, we shorten our networking time.
Okay, so I am roughly about 3/4 of the way done. The rest of the things, depending upon the interest, I can quickly go, because now we are going into what are the new trends. I've been constantly mentioning some of the new trends, but let's go to the unconventional. So until unconventional sprang onto the scene around 2005, 6, 7, 8 time frame, we were kind of doing gas lift conventionally, and we tried to apply some of those conventional trick into unconventional, and then old dogs of the artificial lift will have had to learn how to use the new tricks. And it was very, very hard way, right? So here is a hockey stick picture that shows how the number of rigs exploded after 2007. And not number of rigs exploded, but the percentage of the rigs that were drilling for the horizontal wells exploded. So this red line is the percentage of the rigs drilling for the horizontal well. This brown line is the directional wells, and dark blue line is the vertical wells. And as you can see, that horizontal wells are taking the cake, and this is a global trend, even though here I'm focusing only on the North America. I've been lazy not to update it beyond 2019, but the trend has not changed. So this is change number one. This horizontal well revolution has really made us rethink lots of artificial lift approaches. And by the way, now what you're listening to is some of the slides from my 2016-2017 lecture series under the SPE's Distinguished Lecturer Program. What you're looking at here are distribution of the lateral length, measure depth, and TVD. And when this slide was prepared in the late 2016, what we saw was that on an average, the lateral lengths were close to about 6,000, 8,000 feet long or so. Now, since then, of course, we have seen laterals going up to 2 miles, more than 10,000 feet or so. Actually, here we have some of those, right? And even there are longer laterals that somebody has drilled, but I don't think that has continued. But most of the laterals have stuck to about 10,000 feet or so. So there is a long horizontal section, and then there's a vertical section. So if you look at some of the well geometry, this is what you can see. If you look at the azimuth and inclination profiles, you see that there is a lot of dogleg, lots of changes, twisting and turning of the geometries, wellbore. And that's where if you're trying to lower some lift that has more than 200 feet long assembly, then going around some of these bands can become a challenge. Another thing to keep in mind is that what we call horizontal are not truly horizontal wells. Many of them are classified now as toe up, some of them are toe down, and most of them are what I would call hybrid or porpoising type of horizontal well. And why do I care about mentioning all of this? Because this type of lateral geometry impacts what type of fluid comes into the wellbore, with what velocity they come, what is their constitution when they come to the pumping device, right? I'm not debating here which type of well geometry is better. All I'm pointing out is that because of these different geometries, the artificial lift mechanisms are seeing some of the flow structures that they are not designed to see. If you think about from the perspective, of artificial lift designer, not designer, the person who designs the equipment, what do they assume? They are assuming that you have very well homogenized fluid that is coming inside that device, whether it's a pump or whatever. What horizontal revolution has taught us is that that is seldom the case because of the way we are stimulating the reservoir volume, because of the way we are constructing these well bores. Oftentimes we are seeing the situation where we have large volume of gas that comes followed by large volume of liquid and so on and so forth. And here, this particular graphic that I have purloined from one of the SPE articles that shows, so this is the hill area, and this is the toe area, right? And in between toe and hill, you are seeing some exaggerated undulations. But whenever you have undulation like this, what is going to happen is that in the valley area, you will have liquid accumulation. And then in the peak area or the hill area, you will have gas accumulation. Okay. And then in between, of course, you have perforation intervals. Now, what will happen is that as this valley area gets flooded, then the gas behind it gets built up. And at some point, the pressure of this gas will exceed the pressure that is downstream of the liquid plug. And so it will push that entire liquid plug out and bring it up here. And that is the phenomena we are seeing in this unconventional wells, and now more and more in the horizontal wells around the world. Okay, so these undulations in the lateral is causing this issue, and that issue manifests itself in two ways. First of all, when you look at the longer term impact, what you're looking at here is actual data from some well, and what is the production profile in terms of the gas, oil, water production, what is the total liquid production. And what we are seeing is that even though the time frame is from September 2013 through maybe February 2014, so you're looking at about 6-month time frame, right? And over the period of this 6 months, there is so much of change in terms of the barrels of liquid that passes through that well bore or through that well. Now think of yourself, if you are designing this artificial lift for this well, at what flow rate you will design? Would you consider 800? Would you consider 1600? Would you consider what? This is one of the biggest challenges that artificial lift industry has run into. Not artificial lift industry, artificial lift practitioners have run into with the horizontal well. There is such a severe change in the production profile over such a short time period. Now you may recall that some of the lift methods, in order to change that lift method, you have to call a rig on the well site. And if that is the case, are you going to call a rig every 2 months, 3 months on the well site? Even though onshore rig costs are reasonable, but still it's a lots of hassle, lots of deferred production. And that's what has happened in case of this well. There is a one failure of the ESP here. There is a second failure of the ESP here. There is a third failure of the ESP here. Again, I'm not saying that ESPs are bad. What I'm saying is that because of such severe changes in the flow structures, the equipment are struggling and they fail because, the designer could not envisage all these changes that were going to come to that device's way in the period of 3 months time frame. Traditionally, conventionally, what we see, if you have active water aquifer, you're not going to see much changes in the pressures. You're not going to see much change in the gas oil ratio. If you have solution gas drive, then you will see gas changes, but not such drastic changes. And here, what you're looking at is a short-term change that, and these are the, oh, sorry, I think I did something not I wanted to do. My apologies. I'll share again. I was trying to do something smart and it backfired. Okay, now you should see again my presentation. So what I'm showing you here are the measurement from 2 Eagleford. Well, again, I press the same button. Let me see if I can redo that. My apologies, everybody. How do I go to, am I sharing my screen?
Yes.
Okay, all right. So third time is the charm. Okay, so I'm trying to show you here, there was a multi-phase flow meter that was taken on this well site in Eagleford. And what you're seeing is at 12:14, we are measuring flow rate of 500 barrels. At 12:16, that dropped to 50 barrels. At 12:34, again, it picked up to 500 barrels. Then again, it dropped. So there is a 12-minute cycle, roughly. I mean, I'm eyeballing it here, right? Every 12 minutes, you have big liquid slug followed by big It's very small liquid slug followed by big liquid slug. And here is the another valve on the same pad on the same date we had measured, we meaning whosoever went there to measure it. And what you're seeing is very sharp fluctuations. So the thing about unconventional is that not only you have such a big production changes over longer time period, but you have also instantaneous variations in the fluid rates. That is what has turned the artificial lift design, artificial lift selection, artificial lift operation on its head. So pumping is a big challenge, gas liquid separation is another challenge, monitoring is a big challenge, and back pressure management. So we have begun to realize that as we see the steep production decline in a relatively short time period, we need to plan for a wide range of production rate in a very short amount of time, and large fluctuations in those rates also. Okay, meaning we have to rethink the entire way how we are approaching this lift planning. Now, this is a very complex curve, and I came across this in just a week ago in World Oil. I have attributed here in June 2020, World Oil. There is a very nice article if you're interested in ESP technology, where these people from Schlumberger, they have focused on how the ESP technology has evolved in unconventional, not only evolved in conventional, but also in unconventional. So it's a very interesting case study. But the point I'm trying to make here is that this picture is from Bakken Shale well. In 2015 March, the system curve, meaning this well has to produce roughly about 5,600 barrels of liquid. Okay, x-axis is the pumping rate, y-axis is TDH. Remember our friend TDH, total dynamic head. So they needed a TDH of only 1,600 feet or 800 PSI, roughly speaking, because the productivity was so strong, reservoir was so strong. Within a period of less than 1 month, which is April 13th, 2015, the operating point moved to here, whereby our production, liquid production has gone to 3,200 barrels, and the demand for TDH has jumped to 5,200 feet. So all of a sudden, not only your production volume has decreased, but now reservoir is saying, hey, I need more assistance from you. So earlier, our need for TDH that is shown here was only this much. Okay, and all of a sudden now we need this much of TDH. And then if I go another month into the life cycle of that well, not only the production dropped from 3,200 to almost 1,600, which is 1/2, but the TDH requirement jumped up further. Now it is 6,000 feet compared to what was 1,600 feet just 2 months ago. Now, until about few years ago, there was not a single ESP in the world that would have managed this transition. Most of the ESPs would fall out of the recommended operating range and they will die premature death. This is, the article is about how the ESP technology has evolved, whereby we are able to manage this wide fluctuations in the flow conditions over shorter time period with the same ESP device. But one thing I need to also point out, that this ESP only is working within the recommended operating range, which is shown here in by yellow shaded area, for the time period of about a month. Even though it is operating here, it is not a recommended operating range, meaning more electricity, it is likely to fail faster. Okay, so this is another big challenge. ESP is, by the way, used a lot, but people are thinking that, hey, I need to now be thinking about switching over from ESP at this point, otherwise my ESP would fail. Just over the period of 1 month. And remember I said in some parts of the world, it takes you 90 days to schedule a rig. So if you have to change ESP in 1 month and you do not have rig available, then you have deferred production of 3 months, right? So that's where people have come up with this idea that why don't we come up with a lift life cycle? Meaning you start with a high volume producer like ESP or jet pump or gas lift. And then as the production declines, as the productivity declines, you start using other lift methods like rod pump, piston pump, plunger lift, foam, and so on and so forth. Now, I am not suggesting that this is progression for one well. These are the possible progressions I'm pointing out. For one well, if it's a liquid dominated production, most of the time what people do, they start with ESP, then they switch over to gas lift. At some point they switch over to rod lift. Very recently, not very recently, about a couple of years ago, Occidental came out and their artificial lift chief, who is now SPE's president, Shauna Noonan, she made a statement that Oxy has decided to stick to gas lift, but different forms of gas lift. Start with the continuous. At some point, you go with the gas-assisted plunger lift, plunger-assisted gas lift. Then you go to intermittent lift. Then you go to chamber lift. I did not talk about chamber lift. That's one of the more exotic forms of the gas lift. Okay, so the industry consensus is that we need to be thinking more along the lines of life cycle. If in order to achieve higher profitability, better productivity out of the same lift equipment and not have a lot more failures on our hand. Otherwise it would eat our lunch. And what do we mean by eat our lunch? Our OPEX will go through the roof and will not make any money and we'll have to P&A the well. So that is where artificial lift, on one hand, it helps you enhance the production. It can also hurt you if you do not plan properly, if you do not watch it, if you do not adjust it, right? So one of the lessons that was, and now people are transferring these lessons that we have learned in the unconventional to the conventional, that to bring the continuous improvement cycle. Some of the technologies that are developed for unconventionals are now being applied into conventional to increase the runtime, to decrease the failure rates, right? Because conventional wells also, there are some challenging environment. Until now people said, that is how it is, we'll have to change it. But now people are saying why we should change it. If guys and gals can do it in US of A, why we cannot do it in this part of the world? So that's a kind of interesting shift in the artificial lift approaches. That brings us to the final part of my presentation. Now, even though I said post-COVID-19 trends accelerator, this presentation could have been named as well, what is production optimization, what is digital oil field, and what it brings to the table in the current. Why I added post-COVID-19 trends? Because, by the way, this part of the presentation is from my second distinguished lecture series, which concluded last year. I covered something like 30 countries, 50 locations in that lecture series in each and every continent except for Australia and Arctic regions, right? And that's where my message was that we have to go towards the digital oil field. We have to adapt and accept some of these technologies in order for better profitability. And now what has happened in this COVID era that people have come to accept remote access. People have come to access remote collaboration like what we are doing right now. It is no longer a question, like in some countries, and I would not name names, like they have restriction whereby once you go home from your work, you cannot do any work because you're not allowed to take laptops or any computer equipment out of the company premises. And now the same people are working from home, accessing their corporate resources. So that is more of a cultural shift that is going on. In another country, I was talking to one of the managers and he said that, Rajan, we are only allowing certain people to go to the field because of this COVID related issues. Meaning we are learning to do with less and smaller strength, but remotely, right? And that's where some of these digital oil field technologies are becoming more and more relevant. Like few years ago when I was talking about these things, people would say why I should do it. I am perfectly okay making money. I am making money, so why you are asking me to put in all these gadgets? Another revolution that has been going on is proliferation of personal computing devices. Now all of us are accustomed to booking our tickets or hotels or anything from any part of the world, from anywhere, right? So now people are also becoming accustomed to the idea that, hey, why cannot I learn about my wealth status from my home or when I'm on the road and so on and so forth. By the way, all of these capabilities were there. In 2005, we were watching the wells in Colombia while sitting in our office in Houston. Watching meaning literally minute by minute what was happening, right? But there was still lots of cultural resistance. But post-COVID-19, as I said, post-COVID-19 accelerator is this mind shift. In some parts of the world, people have come to realize that we have to adopt and embrace this, right? So your takeaway from this section should be digital oil field is here to stay. It's not if. Initially people were saying why I should lower this gauge, why I should put things, it costs me money. And now people are saying why I did not think about doing it earlier. Okay. And it's not a question that whether the technologies are there or not. I mean, technologies have been touted by the vendors for many, many years, since last century. Okay. But now they are becoming more mature. The main problem still is that we are not doing a lot more with the data. So a lot more needs to be done with the analytics. That is where I see lots of promise. So we have not realized the promise of all of these digital oil field technologies. Why those promises have not materialized? Because we have not focused on analytics. We have not understood how to analyze some of this data. Actually, I'm right now working on one of a very large project, more than 400 wells, looking at real-time data, streaming in every 1 minute and so on. And I'm beginning to see that how much of infrastructural adjustments are needed. Like some of the data is so unclean, some of the data is so clean. And how do you kind of marry those two, clean and unclean data? How do you arrive at some of the decisions based on that? So the answer is that do not buy into the hype. Keep your expectations reasonable, right? Be happy with marginal gains, right? But focus more on the intangibles like enhanced visibility, better data quality, speed of response, right? Reduce downtime, improved workflow that leads to improved QHSE issues, right? Until now, people were not focused in some parts of the world as much on the downtime or deferred production areas, right? Nowadays, they are becoming more and more aware, especially like if you're part of some of the OPEC group and you are being asked to adjust the production. How do you manage all of that? So this is my thing about post-COVID. So let's talk about briefly what is a production system optimization. On the y-axis, you have $sign, x-axis, you have time. And what you're seeing is the revenue versus cost curve. Whenever your costs start overtaking your revenues, you are basically going to plug and abandon the well, right? We are talking about just the well or the facility. So that is the shut-in time. What if you can come up with some way of lifting the revenue a little bit, okay, as is shown by this dashed line, and drop your cost a little bit, as is shown by the second drop line. So what has happened? You have improved your profitability, which is the distance between this revenue and cost curves. But another thing that most of the people miss, what has happened is that you have pushed your shut-in to some future date, meaning you are doing more with less for longer time period. And this is what people are talking a lot, doing more with less, right? And you have recovered some of the barrels which would have remained in the ground. That is the beauty of some of this production system optimization, or this is the promise of production system optimization, meaning you are trying to maximize not the production, you're maximizing the profit over the life of the well, right? And part of that, byproduct of that could be maximizing the production But more importantly, you are focusing also on reducing the downtime. You are also focusing on minimizing the OPEX, minimizing CAPEX, improving the HSE part of it. Because all of this has some impact on your bottom line, right? So until now, this production system optimization was sold with the promise of increasing production all the time, right? But now we have to be talking about rationalizing production with fewer downtimes, less fatalities, less OPEX and CAPEX. Okay, so basically we are talking about extending the economic life of the field and economic life of the valve. That is how our industry would survive. That is how we will survive personally also, right? So manual effort where we used to send people out to the field to go and read and see whether the valve is working or not. They worked, but you see, one of the biggest fatalities in the oil field that happens when people go behind the windscreen. They start driving in some of the most dangerous terrain, right? So if we can avoid sending people out there, whereby we can access some of the well operations remotely, we can manage the well operations remotely, then we can impact QHSE aspect big time. Not only that, we can also focus on what to do with the data rather than sending people out to the field. So what is the infrastructure required? On the right side, you're looking at different installations, whether it's a gas lift well, flowing well, ESP well, pipeline, or some kind of GC. But you have some type of sensing devices, whether it's sensing pressure, temperature, flow rate, vibration, whatever. All of those data streams are flooding into this box. That box used to be called remote terminal units, RTUs. They could be called controllers. They could be called PLCs, PLDs, or PIDs, loops. Nowadays, people are using another terminology, edge devices. Edge devices is a souped up form of this controller, whereby you are doing more and more number crunching at the well site itself. Traditionally, these devices, RTU devices, were kind of store and forward type of devices with limited on-site control. Nowadays, we are in the ideal world of edge control, and by edge, EDGE. If you have come across that terminology, what we are trying to do is that put more and more powerful processors here who can consume this data stream at higher frequency, who can do some autonomous action, or at least forward that information onward. So how does this boxes forward the information? There is a communication layer. You have either radio, satellite, or cellular based communication that sends this data signal to some data network. Oftentimes now, increasingly, the companies like Microsoft, Google are getting into oil business because they are trying to manage the cloud for you. And not only that, they are trying to introduce this analytics in the cloud for you. There are lots of, and that is one very promising career path for all of us to look into some of those opportunities, in my opinion, right? And I mean, I'm an example of that. I changed myself whereby I'm focused more onto these areas now. So you have this cloud-based networks where you can have some type of apps or applications that is doing number crunching, that is doing some analysis. And then there are people behind that, people sitting in the field offices that are more focused on the tactical aspect of the business, meaning how do I monitor, how do I control, how do I keep handle on the operations, right? Then there are some tactical people, there are some strategic people, field development people, corporate accountants, supply chain people, data management and IT folks. And then in between you have some people who are what I would call analysts, who are engineers, who are subject matter experts. And part of that mix could be also some service companies, service management companies, and so on. So all of this data stream that are generated here are streamed all the way up to here. And you see now I'm using the terminology streaming, like as if we are streaming the Netflix movie. Actually, one of the data transport protocol that is being increasingly used, MTTQ, is data transfer protocol that is being used in Netflix type of technology, whereby we are streaming high frequency, high volume data constantly to the data network. And traditionally we have artificial lift, and I'm digressing a little bit here, please allow me to. Traditionally, we have not been streaming a lot of data from these installations. If you go back, way back in time when I started my career, many wells did not have any sensors. We had those pen chart recorders. Somebody would go and get those charts back to the field. Somebody would try to read those and then make sense out of it. We have come a lot farther, whereby now we are getting the numbers that are automatically entered into our applications, and applications are suggesting that, right? Here's a picture that I have taken from one of the SPE presentations that was about a couple of years ago, where people are showing how they are using this type of dashboards for some value addition in the operations management of a rod pump wells, right? But now the time has come to think about beyond those dashboards. These dashboards have been around since last century, and I'm not exaggerating. Some of the earliest version of computer-aided optimization for operations was in place in Shell in 80s, I would say, or even slightly earlier. But now we need to go from this retrospective dashboard to the future, which is we have to go more into descriptive aspect, which is a visualization. Then we have to go into predictive aspect, whereby we can predict before the things happen. And then prescriptive, meaning what to do about it. And that's where there is significant productivity gains being promised by lots of companies that are coming into our space. Not only our space, all the spaces. This company that I'm working with, Fathom Solutions out of Saudi Arabia, it's a technology startup company. And the same type of paradigms are evolving in that company in different aspects, whether it's a supply chain, whether it's a utility side of it, or whether it's oil and gas. Actually, they are saying that company CEO was telling me that more than upstream, he's seeing a lot more activity in other areas, because everywhere people are embracing this digital revolution. Some people refer to it as Industry 4.0, and that is a big buzzword also. So now here I'm giving you one example, and it's very impressive. That what you're looking at is a SAGD well, and this is an example of how the visualization can help you. What you're looking at is a well bore where you're injecting steam at the surface, and then down below is a producing well bore. So all this steam melts the bitumen, which is being picked up here, and all these yellow dots that you are seeing along the well bore and this red line, these yellow dots represent the fiber optics based data capturing devices. That brings me to another discussion. Fiber optics can capture data to the tune of, in one day, some of the distributed acoustic sensing, DAS, can capture up to 1 terabyte of data per day. Now visualize, we were in the age of charts, and now we have come to the age where we are capturing more than a gigabyte of data. And not too long ago, we did not have even hard disks that were able to capture more than 500 gigabytes. Here we are talking about 1 terabyte of data spewing out of the wellbore every day. That is one of the bigger challenges that I'm working with one of the companies or big operators in the world. So here, what you're looking at is how we are monitoring the temperature of the steam injectors and the producer. By the way, there is an artificial lift angle here, and that's why I included this. There is an ESP sitting here. So this ESP needs to be run in conjunction with this temperature sensing that is going on. So this is a kind of a small example of visual sensing. By the way, some of you eagle-eyed people would have seen that this is from the data of 2010 or so, right? So this has been around for a while, nothing new. Now this is an example that I lifted from one of the papers that I co-authored on Permian gas lift shale. And what we did was we looked at some of the data that was coming out of that condensate well, real-time data. Not only we performed some visualization exercise, but we also did some prediction work, whereby we predicted the static bottom hole pressure, productivity index using using this algorithm that we have put flow here. Okay, and our objective was not to do it statically, but in real time, so that as the data is streaming in, this analysis is being run on continuous basis. And remember what I said earlier, that we have to know what our reservoir is doing. So what is our static bottom hole pressure? What is the productivity index? And these are some of the approaches that allows us to keep our fingers on the pulse of the valve, so that we can make smart decision, fast decision using some downhole gauge data, right? This figure I have purloined from some place, and this is a much talked about topic nowadays that makes a lot of people nervous. Some people get riled up because they do not believe in AI, ML, and some people really get frustrated that they do not know what is going. My objective here is to do neither of this. I am looking at it as a tool set that will add some value to my abilities. I am not right now buying the Kool-Aid or drinking the Kool-Aid that this is going to solve all the problem, but I'm also seeing some tangible cases where this technology can be applied. As I said, there's a lot of snake oil sales going on also. So here is one example that I picked up from this one company's presentation, where they tried to explain how they are using machine learning approach to understand what is happening inside a rod pump valve. So they are selling is effectively a hockey puck shape. If you are a fan of ice hockey, you can visualize what is the size of the hockey puck, right? So hockey puck shape device that they install on the rod pumping machinery that I was showing earlier. And what that device does, it has also edge features in it, meaning it senses how much of load is experiences and where the pump is in its cycle. And based on that, it develops what is called dynamometer card. And by doing some those input analysis, basically they extract the features, meaning they try to figure out what are the important parts, and then they do some of this neural network based work. I'm assuming, I don't know whether they said that or not, but this picture tells me that they must be doing some type of neural networks to figure out whether that rod pump is producing at its design capacity, or whether it is over pumping or it is under pumping. And you may recall when I said that when valve is over pumping, there is a danger of doing what is called a fluid pound that can lead to the failure of the equipment. So if you have this device that can say, hey, your valve is over pumping, so there it can remotely trigger this alert. And then in autonomous mode, it can even decrease the speed of the pumping so that your reservoir can catch up with the pumping speed, right? And that is their main claim to the efficacy of this device that they are touting. And you can see the name of the company. I'm not saying that this is the only device, but this is one of the approaches that is being tried to use some of this machine learning, some of the edge computational concepts to deliver some tangible results, right? And this is the second slide that basically says the same thing what I said earlier, but they claim that they have reduced the number of strokes per minute by 9%. And there is a direct correlation to number of strokes that a pumping unit makes and the energy it consumes. So you can see that if you are going to reduce the number of strokes by 10%, then you are consuming 10% less energy. And in some of these valves where you're not producing a lot of fluid, lots of costs are related to the operating, right? Which is the electricity consumption. So you are increasing efficiency by reducing, but keeping the same production. That's the interesting part of it, right? So you're sustaining 20 barrel per day oil. Production increases, but with the less number of strokes. That is what is the efficiency gain, right? This example I got from another company out of Norway. That's a technology startup. And they are working on a pilot with 4 or 5 operators in that region. Now, this slide is from more than 2 years ago. I have not kept up with where they are now. And what they are doing is again one of those neural network based approach. But this gas lift, it is optimizing gas lift. Now, gas lift problem, when you're trying to do on the field wide basis, it can be very complex optimization problem, because you're trying to simultaneously solve so many linear equations that some of the current traditional optimization algorithms really do not do the job. So their approach is to use some type of artificial intelligence whereby you narrow down the number of decisions to few using, and that way you arrive at, okay, what are my system bottlenecks, where I need to inject more gas, when I need to inject less gas, and do it dynamically. As they mentioned here, they are looking at around 400 variables, 400 knobs that you can twist and turn in order to dial in the production, right? So that is another example. Now, I gave you some glowing examples of how efficiency, but now I'll show you some ugly side of some of this data management side. And this one has come from a presentation from ConocoPhillips from a few years ago. And they started on this journey, and what they realized is that because of the legacy infrastructure, you have same data sitting in different databases that are managed by different groups who have different responsibility, meaning it's what is called distributed data structure. When you have distributed data structure, meaning everybody and nobody is in charge of managing the fidelity, whether the data is good or not. So, and I am seeing that day in and day out in my practice where reservoir engineering is working with one number for reservoir pressure and production has another number, whereas they could have derived a better number using the gauges that they have, right? So this is just a small example. So what ConocoPhillips did is that they are saying that we are moving over to the data integration platform, whereby all the data goes into the same platform. So there is what they call single source of truth, meaning everybody is using the same data, consuming the same data. So if there is an error, it is caught and fixed in one place, not in 15 places. So rather than having a spaghetti of data strings lying all over, you have a very streamlined process. And this is what is a must if you are going for digital oil field based approaches. Not only data needs to be accessible, but it needs to be integrated, it needs to be validated, and so on and so forth. So this brings us to some of the digital oil field related implementation caution that I pointed out. The data is not always what it seems. Sometimes people make mistake. They do not understand where that data will be consumed. So there is no validation in place. So for example, sometimes people enter the wrong depth of the pump. And it is happening a lot more than what I would like to admit or people would admit to, right? They put a different model of the lift equipment than what they said that they have lowered. So here you're doing all of your simulation based on what your design sheet says, but in reality, you have different. So somebody has to really focus on some of these data quality issues. Or we have to have analytical paradigms that can accommodate for these large errors and inaccuracies, right? And this is another thing, human element. John is trying to sell round wheels and people have been accustomed to using square wheels. So they said, no, we are too busy. We cannot try out your new technology. And they missed the point. So one important message that I often give is that until and unless company leadership is behind it, any of this digital oil field, edge or AI or ML initiatives, they typically remain either focused in one part of the company or they fail. And that's where this collaboration centers is another. I just inserted this picture. Nobody is wearing mask because this is from predate and this is marketing literature. But the idea is that being able to have access to people who are in different parts of the world with different knowledge base is a must. as I pointed out, in order to understand artificial lift, in order to analyze, in order to design, in order to operate artificial lift, you require multiple discipline knowledge outside of production engineering. You have to know electrical, you have to understand data structures, you have to understand machine learning and whatnot. So, and not a single person can capture all of that. That's where the collaboration is must. So we have numerous success stories out there. In spite of what I said, there is a better and better data capture and transmission occurring. There is a software integration occurring. AI, ML, edge devices are invading. Are we ready? Are we ready to evaluate them? Or are we going to take it on the face value of what vendors are selling us on? And that is where I would end my presentation. Sorry about making it such a long presentation. As this monkey says, questions are guaranteed, but my answer may or may not come. So thank you very much again for this opportunity. Now we can have some question answers.
Thank you so much, Rajan. It was a wonderful presentation, even though it was a little longer than you originally designed it to be, but that's fine. I mean, those who are dedicated people, they will hang around. And so should we go to Q&A session now just to see what are the questions out there? Hello?
Yep. You're asking me?
No, I'm asking our attendees as well.
Well, I suggest we do, in order of importance, why don't we let Rajan pick those questions that are, if in case we run out of time, why don't we let Rajan choose those questions that are really, that would be of interest to the majority of the audience.
Okay, let me see. How do I bring up the question panel?
You have to go to the chat session and then where everyone look it up over there, unless some of them posted it directly to you.
No, so I'm trying to bring up chat. At one point I had chat open and now it has.
I can go through it. I'm right there.
No, I need to look at, oh yeah, here we go, chat. Okay, yeah. So, this is, so which gas loop system is the most friendly to sand, and would you trust it to perform well, or would you suggest to add a sand control scheme? Okay, it's a generic question, and I understand Delta Screen is one of the like a provider for the screen. So there is a value of having the screen, but the main draw for gas lift system is that it is somewhat agnostic to the presence of sand, and agnostic in the sense that there is no mechanical device inside that gets impacted. All we are trying to do is reduce the density, right? So some people say that, yeah, you don't need to do much about it, but depending upon the amount of sand that is coming, you may suggest some sand screen or whatever sand control devices that are available out there. I have not kept up with them. So in what case would you run dummy valve and what case live valves? Okay. So this is a long-term planning question. So some companies, they say that my workover costs are so much that I do not want to call the rig again and again. And this dummy and live valve question only comes for mostly when you have side pocket mandrels. So if you are expecting that your operating point or the fluid level is going to go down, then you may want to lower some dummy valve to begin with at a different depth. There is a procedure called bracketing. So in that, you may start in the bracket some dummy valve, and then as the time occurs, you can substitute them with the live valve. I think that is where your question was going. Dummy valve are often used also during the initial installation integrity test, when you do not want to damage the actual valves, and just dummies are nothing but a solid piece of metal that provides the isolation between casing tubing annulus and tubing, right? So that is my response to that. Okay, let me see. I think I jumped in between.
Are you reading up the question that has been posed directly to you?
Yes, no, I'm looking at the chat and
But it is to address to you directly or to everyone?
this one is to everyone.
Oh, okay.
Okay, I do not, let me see, is there any specific one? I
Are
do
you
not see.
coming from the top to bottom?
Yeah, I did not realize that I was somewhere in the middle. Okay, so let me go to the top. Salim, you said if you had gas lift for a valve, why did you have to change to ESP? Was it because of a design flaw? Okay, so typically gas lift to ESP decision, I have seen that happen in quite a few cases because gas lift becomes prohibitive to operate once your water cut goes beyond a certain value, or you do not have sufficient amount of gas available into the field. And if you continue to lift, let's say 90+% of water, and I have seen some wells that are producing 10, 15,000 barrels per day and 90% of water. So the oil is still valuable, but then you cannot supply enough gas because you have double whammy going on here. As more and more liquid comes, your gas production goes down, right? Because your gas cap is exhausted, or there is a strong aquifer, water aquifer. So in a way, your point is correct that it was a design flaw, but design flaw in the sense that it was not properly planned. Or maybe people said that, yeah, we'll operate this field on gas lift for first 10 years of its life, and then we'll switch over. Sometime it may happen that you put gas lift because you do not have electricity infrastructure and you're waiting for the grid to come, right? So there are a variety of reasons why one can switch from one to another lift method. So there are some of them has to do with reservoir, some of them have to do with the logical constraints, operational constraint, and so on. Sometime there is a new operations manager, and in her previous role, they were using more ESPs. So they said, why we are not using ESPs, guys? So that is the reason. Next question.
But if you, Rajan, just one more point over here. If you have a well with a high GOR, are you going to go switch to ESP?
Not necessarily. But again, this high GOR, it's a very interesting debate. People often look at the high GOR. I say that no, you should look at what is the free gas at your pump depth. Because nowadays we have ESPs available that can handle up to 20% by volume free gas at the pump depth without any even separation. And some of them have gas separation devices available, whereby theoretically speaking, they claim that you can go up to 70% void fraction, 70% by volume gas. So the answer to your question depends, Salim, in what is your appetite for going in. First of all, you have to understand how much of free gas is there. Don't go by just GOR. Okay. What is the pressure at the pump depth? Is it above the bubble point pressure? Then you have 0 GOR that your pump is going to see. Correct?
Yes.
So that is the reason, I would say. And even if you have free gas, you can still handle it. And your ESP vendor would be happy to give you all kinds of gas separation devices that can handle the gas.
Oh, I see. Okay.
Okay.
So regardless of whether it is a free gas is 20% or 80%.
Yeah, but I mean, if I was operating that asset, then I would take a harder look at it. That if I have higher and higher gas content, what is the likelihood of me having a pump failure because of what is called cavitation phenomena that happens with the higher gas content, or what happens when I have a pump off situation. And in pump off situation, basically your pump is filled with the gas, meaning it cannot pump anymore, right? It cannot provide any more TDH because gas is compressible. And there are a variety of solutions that vendors have come up with, and all thanks to all of these things that are going on in the unconventional area, whereby the variable speed drive has some smart algorithms built into it, whereby it can slow down the pump and let the gas either bypass or gas pass through the pump, and then they speed it up again. So there are possibilities are there. but you have to, I cannot give you one generic answer that will satisfy all the needs. We have to look at a particular situation. Next question is from Francisco. Would you suggest to run artificial lift in a deep water well? If yes, what type and why? Actually, yes, people have run artificial lift. Basically, whenever you are lowering any pump, it's an artificial lift, right? So one of the longest running pump that I came across, ESP, was in UK. And why it has been longest running? Because all it has been pumping is water. And it was a deep water well. And as you can see, water is a somewhat benign condition in the sense that you do not have temperature issue, you do not have CO2, H2S type of issues. All you have to worry about is the scaling tendencies. And so, yes, answer is yes. Can you please clarify, this is Rafat's question, can you please clarify what you mean by ESP has the most capital? I think Rafat is not on the call, but I did answer when he was there that most capital meaning per annual, on annualized basis. Next question is Salim. You talked about tangent section for ESP. Can you expand? Okay, so I was talking about tangent section for ESP in the context that you can see when ESP can be a very long slender device, 100+ feet long, right? And if you are trying to lower the ESP in a deviated section, and if there is a sag in the deviated section, rather than a straight tangential section, what is likely to happen? Your ESP assembly would kind of sag in the middle. If it is sitting in the not straight section, that would lead to the housing, not only housing being bent, but the shaft stiffness might be impacted, your impellers and your basically the pumping mechanism not working as it should. Because if you think about it, the ESP is working on the basis of everything running concentrically. And now all of a sudden you have eccentric movement occurring. And that is what leads to the higher failure, lower frequency, lower efficiency. So that's why I would say that you need a tangential section which is straight for ESP. The next question from Salim was, what is foam lift? I think that has been answered. You are basically inserting some kind of surfactant which creates a foam as it makes. How it works, where is it best applied? Salim, did the presentation answer some of your question about where it is applied and such?
Yeah, I think so. Yeah.
Okay. Next one is, what percentage of gas lift gas you can recycle back? That's a very good point. So this is typically thumb rule says that about 2 to 5% of the gas that you lose. And where do you lose it? Remember, the gas goes back into the solution depending upon the saturation of the oil. So part of the gas can be lost because of that. Then on the surface machinery, as it makes round through the separation, and then it goes into the compressor intake while it goes through some time heater treater. So there are so many equipments that the gas traverses through that you are likely to lose some of the gas, and estimate is anywhere from 2 to 5%. That is called a makeup gas that you need to put back. Okay, on an average, how long an ESP function before replacement is required? This is so field specific that I'll give you some statistics, and it's not something, I mean, it was shared privately, but since then it has been published also. So like in case of Saudi Aramco, for example, they are running some of the most expensive ESPs in the world. So they are impacted because of not only deferred production, but also because of the cost. And they say that their pumps last anywhere from 3 to 5 years. And their goal is to make the pump last 10 years. Now they admit that it is a holy grail, right? I am working on some of the ESP project, not with Saudi Aramco, another company in that region. And I see the pumps that are lasting as long as about 7 or 8 years. And then I have also seen a pump that are infant mortalities, meaning within 4 or 5 days the pump conks out, or even while they were turning it on, it conks out. And most of those are related to the installation time operational defects or defects caused at the installation time. Okay, so there is not a single answer. And by the way, people ask me this question all the time about all the artificial lift method. And I said it depends. In some parts of the world, if PCP runs 3 months, people go out and celebrate and have their beverage of their choice. And in other parts of the world, if it dies in 3 years, then somebody's hand gets strapped. So it's so situational specific. Which gas lift system is the most friendly to say? Okay, I think I already addressed that, Francisco. Next presentation, many thanks. Thanks, best of luck, thank you. I think, okay, here is a Salim's question. Have you heard of gas lift in unconventional? Oh, of course. I have actually worked on quite a few wells, unconventional gas wells that are using gas lift. But, huh?
Why?
Okay, so some of those gas wells produce a copious amount of liquid, lots of liquid, and gas is readily available, right? Or on the same pad, you may have another, and this might be a po' boy gas lift, for example. And what do I mean by po' boy gas lift is that you just bring some compressor on the well site and you have a very rudimentary separation facility. You take a gas stream and then just bump up the pressure by few hundred PSI and then inject. So that because of the higher volume of gas passing through the same cross-sectional area, what you're doing, you are essentially not only swabbing the well, but also you're keeping the velocity above the critical velocity. So actually gas lift is very, very popular in unconventional space, not only in liquid, but also in gas dominated production. But there, more often than not, you will see plunger lift or plunger assisted gas lift or gas assisted plunger lift. Okay. So
that means most of these are happening in Eagle Ford, I mean, I guess.
Yes. Particularly condensate window.
Condensate, yeah.
Yeah. Well, I was in Marcellus for some talk, and I did find that they were using gas lift there also.
Because they also have a liquid condensate portion as well in some of the places.
Correct.
Some of the areas. Yeah.
Okay, the next question was from Lee. Do you have example of combining gas lift and plunger? Yes, as I said, plunger assisted gas lift or gas assisted plunger lift is often used. And that is very important when you do not have sufficient reservoir energy or sufficient reservoir gas that is coming. I mean, the gas is coming, that is still valuable, but it is not in high enough quantity that it can drive the plunger. In that case, you are assisting plunger to rise and take the liquid above it using the gas assisted plunger lift. And that is primarily in the liquid dominated production. If you will do the literature search on gas assisted plunger lift or GAPL, GAPL, or PAGL, PAGL, then you will come across plenty of the examples of that. In the steam injection huff and puff, this is from Abdul Malik Haider. In the steam injection huff and puff method, my understanding is the production is not continuously and it has to follow certain cycle. How does the steam affect the gas lift in this case? Very good. So Abdul Malik, in huff and puff or CSS, cyclical steam stimulation, most of the time you're right that the production is not continuous. And people do not use typically gas lift, though you can potentially use it. Most of the time people use rod pumping methods in that case, because this is a highly viscous production. And one drawback of gas lift is that it doesn't work well with highly viscous production because of the viscosity and the drag forces, the gas does not get dispersed as well in the viscous production. Now you can make argument that, hey, I already injected steam, so the viscosity has gone down. But typically people use pumping methods, which is, and rod pump is a method. There are special devices that have been developed that work in conjunction with rod lift. So whenever you are in the huff period, meaning you are injecting steam, you can lift the rod in such a way that it basically allows the steam to bypass the pump and goes into the formation. So that is my response. Does it answer your question, Abdul Malik? Or do you have follow-up?
But okay, but intermittent is only in case of cyclic steam stimulation, half and half.
Correct.
But in SAG-D or steam flooding, there's nothing called intermittent, right?
Correct. So now let's talk about SAG-D. So in SAG-D, people have tried, again, I'll use this po' boy gas lift, but most of the time it's ESP, because the problem with the gas lift is the same thing. What happens is, in case of, now I'm going to say something and I'll contradict myself in saying that, but what I have been told is that getting a reliable lift efficiency with gas lift in SAG-D is very, very difficult. And you require a lot more optimization, ongoing optimization in order to make it work. And that's why the preferred method most of the time is ESP, unless the valve is a marginal and they do not have electricity available readily, which is a kind of highly doubtful, because you have to generate steam, right, at the site. So most of the time there they use what is called po' boy gas lift, which is just they push the gas down. And the second problem in SAG-D is that you do not have that much of free gas because it's a viscous production. There is no gas to begin with, right?
Exactly. Yeah.
So that's another challenge inside. So that is my answer.
But isn't that, Rajat, in the SAG-D, mostly in Canada, they're using PCP because of a lot of sands production as well?
Okay, so now, not with SAG-D. Now, unless you choose to use non-elastomeric stator, meaning steely stators. Okay, so in Canada, there is a PCP is used for cold production.
Cold production, yeah.
Not for SAG-D, because the problem is the stator, we do not have elastomer that is able to handle 500 degrees Fahrenheit or so.
Okay.
That supersaturated steam typically brings with it, right? Especially if you have steam breakthrough. Now, in cold production, definitely they use PCP. And people, when they try to use still or non-elastomeric stator, the problem there is that the clearance between the stator and rotor has to be so fine-tuned that it does not get gas locked when there is a steam breakthrough occurs, or whenever there is a viscosity changes that happen, then the pump characteristic change. So it has been talked about, but not tried.
I see. Okay.
As much in my experience.
Thanks.
And again, my apologies for really getting into the networking hour and making it a very, very long
No, that's fine. Well, I don't know. We're going to go for networking sessions. Are there other questions remains to be answered? Well, overall, Rajat, in terms of capital expenditures, I mean, there is a CapEx and OpEx. The CapEx is highest in ESPs. What about the OpEx? Is that more in gas lift, or which one do you think?
Okay, very good. Unfortunately, we do not have a very reliable answer, because even I can argue that CapEx can be also very high in case of gas lift. If you have a centralized compression system, then you have to lay the pipeline network and such. Another thing is that gas lift is not the most efficient lift method. It is considered a noble method, meaning it will work under whatever conditions. But the best efficiency that you can get with gas lift in terms of lifting efficiency is less than 40%. Whereas ESP, properly tuned ESP, can deliver upwards of 50–60% of the efficiency. Now, having said that, as you saw, some of the ESPs, when they are operated far outside of recommended operating range, their efficiency can drop as low as 12, 14, 15%.
Mm-hmm. You mentioned about the ESPs, it can work on different ranges, etc. But on the other hand, when it is a lower end of production, when ESP capital cost is so high, why would you think about using ESP rather than something else like plunger left or rod pump?
Yes, so this is a logical choice, but oftentimes in the earlier exuberant days of unconventional, what people were looking for were IPs. What is my first 30 days production? And ESP, and that helps me lift up my company evaluation, right? If I go to the market and say that, hey, I drilled this well and I'm producing 9,000 barrels per day. My 30-day IP is 5,000 barrels per day. All of a sudden, my reserves valuation goes up. Now, nobody's going to go back and ask them that, hey, what is your 90 days IP or what is your 1 year IP? Okay. Yeah. So there are some lessons that we have learned, which people do talk about in those lift forums, that when you let it rip like that, you are going to close the fractures and you have lots of near wellbore damage. So we have now, I think, come a long way from those days. So people are not making those rash decisions like we used to. And we are getting more rational issues like what you raised, that why I would put that. So I'll tell you, I was sitting across from one company in Oklahoma City about 2015 timeframe. And they were saying that, yeah, we are ordering ESPs. And at the same time, and that, if you recall, 2014-15 time was go-go era, right? Everybody wants all the equipment now and lower and go get it. So he said that we are ordering your rod pump equipment at the same time when we are ordering ESPs, because there was a longer back time for rod pump equipment. And their strategy was they would lower ESP, they would keep it alive for 2 months. And this is Bakken. They would keep it alive for 2 months or so. Keep it alive, meaning keep it in the hole. And then after 2 months, a rig goes to the well site, pull out cable, pull out the ESP, pull out string, and then lower the rod pump. Right? That is what they learned hard way. Nowadays, people are saying that I do not want rig to go back at all. So why don't we start from the gas lift from the day one, and then maybe after a year and a half or 2 years, we'll talk about doing rod pump. And companies like Oxy, what I said earlier, referring to Shona Noonan, they said that, hey, look, because of these deviations and all of that, we have so much of rod breakage going on and our operating costs are higher. So we will not go rod pump route. So your takeaway should not be that one is bad or good. It is just a company specific decisions that they make depending upon what are their expectations on ROI and such.
So they're not going to go to rod pumps, so they're going to stick to gas lift as long as they can?
That was the stated presentation philosophy more than 3 years ago now.
Oh, I see. Okay. Interesting.
Yeah, so there are, I mean, you will find naysayer on both the sides of the aisle.
Have you worked in Barnett Shale where there's a lot of gas? And
I have not, no. Honestly, lots of my work is more overseas than in the unconventional was when I was with Weatherford, and we were looking at some of the data and more into educational and doing some of the ad hoc consulting work when I was with Weatherford.
Because I was strangely, Rajan, I worked in Barnett, and I found one of our production engineers who was hired after I joined there. And he was contemplating to use gas lift in Barnett, where it is 98% is oil or gas production. So I couldn't figure it out why he started to use the gas lift in there.
No, I tell you, Barnett Shale had lots of gas lift now that you tell me, and that is based on my interaction with my colleagues who are working on the gas lift business in Weatherford. So I had some examples from Barnett Shale on gas lift.
But it is only where there would be a condensate, right? But if there's no condensate, why would you use a gas lift?
You can have lots of connate water.
Oh, connate water, I see.
Right? Or
yes,
so I mean, it is not only condensate, but you may have water that is vaporized and then it might condense or come back, or even you can have a strong aquifer that is pushing the water also.
I see. Okay. Okay, that makes sense. Okay, thanks a lot.
All right, sure. Any,
We have only 15 minutes to go to a networking session. Do you really want it? What about the other people? Well, I see the
as
Francisco.
of now, we have 7 people, and Ryan, nice to see you again, and thank you for your help with describing you to Salim for that SPE. SPE is another organization that I feel very strongly about, and
Yes, I do.
so I'll try to involve as many people as possible whenever those opportunities come up.
Mm-hmm. Thanks a lot for that as well. Yeah.
Yes, Francisco.
Ryan, thank you. Excellent job. You are an excellent professor, teacher, presenter. Your presentation was ultimately clear. I think we all enjoy ourselves.
Yes, exactly.
Say goodbye, and I'm going to start processing the recording of your presentation. If you want,
Thank you so much again.
we are going to upload it to our YouTube. But
Mhm.
also, if you would like it, I can send it to you in any other format.
Oh, no. If you can just share the link, that will be fine. That will be just my 2 seconds of glory, if I may call it.
All right, well, thank you.
Thank you again. Thanks for your question.
Anyone has any other question? Because it's less than 13 minutes. I don't think we need to go to a networking session. Yeah, unless you want it, I can do it. Then I have to be the host, Francisco.
I'm leaving. I gotta do some other stuff.
Well, then you turn me to be the host. Then you can leave.
I'd be glad to do that.
Otherwise, I can't take the individuals to the networking session.
Okay.
Yeah.
Well, I'm going to step out. Rajan, I appreciate your presentation here this morning. Was fantastic. And thanks to yourself, Salim, for helping organize this all.
Oh, no problem, Ryan. It has been a while since we last spoke.